Hey everybody, this is HVAC design for the real world. The first part of this recording is actually a re-recording because when I taught the class last Thursday, I forgot to hit record for like the first 45 minutes. So I'm going to re-record this, and then at some point you'll kind of see it jump into Russ King's presentation of how Manual J works with Quick Model 3D. So we're going to jump right into the class. I'm going to share my screen. All right, so yeah, that's a little bit of information about me. Of course, many of you probably already follow me on social media. Here's my company, Comfort Science Solutions, and it's more of a consumer end user, homeowner facing business. So you may want to follow that, but most of my HVAC content that's for contractors and technicians is going to be this right here. I also wanted to bring your attention to the Better HVAC movement. Here's the website, betterhvac.org. This is rather new, but most of you or all of you are here because you care about your HVAC career. You want to do better work. And that's really what this organization is all about. It's really a grassroots organization of professionals like me and other pillars of the industry that have been doing this a lot longer than I have. But this is where you can get better education. And actually, if you're a contractor, we're going to be having a not only a contractor facing website, but also a portion of it that consumers can go to and get educated so that they're driven to contractors like you and I that just do better work. So check that out, betterhvac.org. Russ King joined us on the class. This is a little bit of information about him. Russ is the founder of Quick Model 3D. It's an HVAC design software, and you'll be able to see that process later on in the class. So stick around for that. That's how you can get a hold of Russ. But let's talk about what we're going to go over in the class. We're going to talk about what a manual J is and understand how heat transmits in and out of a house, heat gain, heat loss, and what we need in order to gather information for a manual J. Then Russ will get into how Quick Model 3D makes the manual J process a lot easier because you can actually draw the house, trace it over a set of plans or a sketch that you made out in the field, and it really comes to life in 3D. Then we'll get into Manual S. Manual S is system selection and how we select equipment that are within the tolerances of Manual S. We'll get into sizing heat pumps, especially for cold climates, because there's new information from the latest Manual S that just got released, as well as sizing dehumidifiers. And then we'll get into Manual D, which is duct design. And of course, there's a lot of rules of thumb when it comes to duct design. We'll get into why some of those are actually helpful, but where we need to be careful about just using rules of thumb for everything. And again, this class is not a complete soup to nuts on the ACA design process. What it is teaching you what you need to know, concentrate more information on so that you can be accurate, and maybe some things that aren't worth as much of your attention, things that may be more in the category of splitting hairs. Manual D is all about friction rate. We'll talk about friction rate and why we need to give an appropriate amount of attention to friction rate, but we'll also see that we don't want to spend an unreasonable amount of time on friction rate because at the end of the day, we're looking at a design, a duct design, and a duct size. And the friction rate does drive that, but we'll see just how much it actually drives it. All right, and then Russell showcase how Quick Model 3D makes duct sizing and the layout visual for not only you, but your customers. The ACCA or ACA design process starts with Manual J. J stands for joule, which is a unit of heat in the science world. So we talk about heat gain and heat loss. Then we go to Manual S, which is HVAC system selection, where we're matching equipment to that heat gain and loss. And then we get into duct design, Manual D. Here are some other people that you want to look into if you haven't already for additional training. This is where I go for training. I don't really feel worthy to be counted among these elites of the industry. And when I say elites, it's not that they're not reachable. It's not that they're not approachable. They are very approachable. They'll answer any question you want, but they are just at a completely higher level than what I'm at. So one thing, the NCI organization, National Comfort Institute, they specialize in delivered capacity, airflow, combustion analysis, air balancing. Really great organization to learn about airflow and combustion. Alex Meany from Mean HVAC. He used to work with Rightsoft and now he is a solo consultant and trainer. Ed Janowak, he now works for ACCA for a few years, but he's got a lot of educational content out there. Allison Bales with the Energy Vanguard. He's got a book, A House Needs to Breathe, or Does It? And that's a great introduction to building science and high performance HVAC. And finally, hopefully all of you are already subscribing to HVAC School, their tech tips. You're looking at their webcasting and their podcast, listening to their podcasts. That is a great resource for anybody in HVAC or refrigeration that wants to get better. So let's get right into Manual J. What is heat? Well, heat is energy. The unit that we use here in the United States for heat is British Thermal Unit, or BTU. So just to kind of put that in context, 1 BTU is about the amount of heat that a match produces. And so that may not seem like a lot of heat unless you are holding that match under your hand. And then all of a sudden that seems like a lot of heat. And that brings us to temperature. Temperature and heat are two completely different things. They're related, but temperature is the intensity of heat, but not heat itself. So to put that into an illustration, let's hold that match under a spoonful of water. Do you think that match will affect the temperature of that water? Yeah, it probably will. By the time that match goes out, that water might even be pretty warm. But let's hold that same match under an entire pot of water. Could we expect to boil that water with 1 BTU? Absolutely not. And that's just because the intensity of the heat is spread out over a larger area. So again, we want to understand the difference between temperature and heat because we deal with both at Manual J. Heat gain and heat loss, the cardinal rule, it's one of the laws of thermodynamics, is that heat travels from warmer to cooler. So when we talk about heat gain, we're talking about heat trying to get from the outside to the inside. Heat loss happens in the winter because it's warmer inside than it is outside. So we would have heat loss going to the outside. Both cases, heat is traveling from warmer to cooler, less cool to more cool, less cold to more cold. Just whatever that relationship is, heat is always going to travel from where there's more heat to where there's less heat. And that is just the universe trying to find balance. Heat load calculations measures how much heat enters and leaves the building per hour. So we're talking about heat gain and loss. And we measure that in BTUs per hour, or BTUH. ACCA Manual J is very useful, but there are some limitations. For example, we only want to use this on residential low-rise buildings only, so we wouldn't use that on a commercial high-rise. If we have a zone system, Manual J needs a little bit more help, and that's where some of the other ACCA manuals, like Manual ZR, comes into play. So you can't expect Manual J to work out 100% for you without using those other manuals in the zone system. A block load is a term that we use when we consider the entire building as one room and it's served by one HVAC unit. And so when we are doing an equipment change out, just a like-for-like replacement, we are required to still do a heat load calculation, but it's acceptable for us to only do a block load. But a more accurate heat load calculation is a room-to-room load. And that's really required when we're doing a new build, maybe a ductwork replacement, where now we need to know how much airflow needs to go in each room. The only way we can do that is do a room-to-room load. And if we use software, and I always recommend that you use software like Quick Model 3D, for it to be powered by Manual J, to have that official certification approved by ACCA, then it needs to go through rigorous testing before getting that. And not every load calculation HVAC design software can say that. Not all of them are ACCA approved and certified, powered by Manual J. So be very careful with that. But Quick Model 3D is. So let's talk about heat gain in a little bit simpler way. Here we have a cheapo cooler that you might get from a big box store. Just maybe it's a $5, $10 cooler. What are some factors that affect the load, or if we're thinking about the cooler, how much ice or how many ice packs that we put in that cooler? Well, one of the main things is what are we trying to cool? What temperature are we trying to maintain? For example, it's very critical to be able to maintain a certain temperature if your lunch is egg salad, because you don't want that egg salad to get too warm and spoil. But if you're just cooling a bag of Doritos, then it probably doesn't matter if that cooler gets a little bit warm. So you may not throw in as much cooling or as many ice packs in there. But with egg salad, you want to make sure you keep that refrigerated. You're definitely going to give a lot more attention to that. And that really has to do with the indoor design temperature in our manual J process, because we're trying to achieve what has been considered a acceptable indoor design temperature, which we'll talk about in the next slide. Outdoor temperature is another factor. Are we setting this cooler out where it's hot outside, or is it only in the 30s or 40s outside? Well, that's going to go into our decision about how much ice or ice packs to put in the cooler. Is the cooler going to be sitting in the sun or shade? Because even though it's only 40 or 45 degrees outside, if it's sitting in the sun, that can warm the cooler up just as much as if it was a hot day. So we've got to keep that in mind. And the same thing with a building. There are certain sides of a building that sit in direct sunlight. Others that sit in the shade, and the amount of heat gain and heat loss, or heat gain in that case, is very different whether it's sitting in direct sunlight or whether it's shaded. And the cooler construction quality. There's a big difference between the cooler shown here and something like a Yeti cooler. The Yeti cooler is going to have better insulation. It's going to be better sealed, and so it's going to keep your lunch cooler for a longer time. It's going to take longer for it to warm up, and so maybe you don't have to worry about throwing as much ice in there. Factors that affect heat gain and loss. So again, we talked about the inside temperature. Indoor design temperature, according to Manual J, this is our target summer indoor design temperature, is 75 degrees Fahrenheit, 50% relative humidity. And if you've ever thought that 75 degrees Fahrenheit is not cool enough, then it's probably because you weren't controlling humidity well in that building. And so the building felt warmer. But I'll tell you, I keep my house at 75 and 50 because it's a well-designed, well-performing house. And sometimes I actually have to raise it up in the summertime to 76 because I actually get cold. In the wintertime, our indoor design temperature, or our target set point for a thermostat, is 70 degrees. Now, we don't really worry as much about humidity in the winter. I mean, we do care about it, but ACA does not give us specific guidance on that. We're allowed to have a range because winter humidity can vary according to a lot of things. And one big factor is also the climate and the latitude, and also the altitude that we're in. So there's a big difference between having a home in Florida and having a home in Maine. So as far as our summer and winter design temperatures, that's going to make a big difference. So we have to put that in the heat load calculation software. And finally, the building orientation and shading. The sun has a huge effect on the heat gain of a house. And so we need to make sure that we model that in the software correctly. And the construction of the house. There are high performance houses, and then there are low performance houses, and everywhere in between. And so we have to understand what the R values, the insulation levels I'm talking about, how well the house is built, how well it's sealed. There's a lot of factors that go in there, and especially when we start talking about things like thermal mass, which is the ability for a building to kind of hold and slow down the transfer of heat. Ducts, the location and the quality of the ducts. Obviously, there's a big difference between ducts in an attic and ducts in a conditioned space and how much heat that they gain or lose. So if you go out to do a site survey, to do a manual J, if you're old school, you can bring a clipboard and a pencil. I always preferred an iPad. I used apps like Notability, which allowed me to overlay a PDF or a floor plan, or even draw a floor plan as I measure it. But also I could highlight and use different colors and just have a little system that I used to be able to differentiate my lines that I was drawing and other notes that I was taking on that project. But you're going to want to have as much information as you can before you even get there. So I always used to pull, if possible, the footprint of the building. That was available from the county tax website. Sometimes you can get that from Zillow. You can pick up things like the square footage of it, how many bedrooms, the orientation of the building, because you can pull it up in Google Maps. So you can already have that information before you get there. And also bring things like pencil or highlighters if you're doing it by hand, tape measure or a laser measure. But I tell you, a great app that is now available is Cubicasa, which allows you to take your cell phone, scan the walls, the interior of the house, and it gives you what looks like a professional architectural footprint, room layout of the house. And then you can actually upload that into Quick Model and go from there. So that's a really great tool. And things like a thermometer or a hygrometer to measure temperature and humidity in the house, just to see where the house is at, especially if you're going in the dead of summer, dead of winter. Be observant and ask questions, because the occupants of the house is going to be your best source of information, but you do have to ask the right questions to get the information you need out of them. So what we're going to be doing today is taking a sample house, which is the house that I built last year here in Southport, which is near Wilmington, North Carolina, by the coast. And what I want you to do is take a look at this house. Here you see pictures of it. It is a 1,600 square foot house close to Wilmington, North Carolina, 3 bedrooms, 1 level. It's on a slab. I want you to think about what size unit, just by looking at the house. And again, I'll show you a picture of the house again. What size unit would you say needs to go in this house? And store that away in memory, because we're going to come back to that. Let's go back to indoor design or design conditions, talk about indoor and outdoor design conditions. So in any load calculation software, the mandatory indoor design conditions that we want to use, now we can override them, but it's not recommended, are the thermostat set points. So 70 degrees in the winter, 75 in the summer, 50% relative humidity in the summer. The outdoor design conditions are going to vary with what city that we're in or what area that we're in. And so we have to look those up. Usually design software that's powered by Manual J just has you select that, and it has all those conditions already pre-built. But the outdoor winter design condition, if you see this 99% right here, what that means is that it's only colder than that temperature, in this case, 27 degrees, 1% of the time. So we are never designing our system for the most extreme hot or cold day of the year, because if we do that, we will always be oversized all the other times. In the summer, they call it the summer 1% design condition. And again, that just means that it's only hotter than that 1% of the cooling season. Other terms you may want to be familiar with is heating temperature difference and cooling temperature difference. This is the difference between outdoor and indoor temperatures. So say, for example, it's 70 degrees in the winter, 27 outside. My heating temperature difference is going to be 43 degrees. A much colder climate, but maybe it gets down to 5 degrees in the winter, would have a 65-degree heating temperature difference. And that matters as far as how quickly that house cools off. And then the same thing in the summer, cooling temperature difference is our outside design conditions minus our indoor design conditions. We don't see as much varying here in the United States. Most climates, you're going to see an outdoor cooling temperature or outdoor design temperature of somewhere maybe in the high 80s, low to mid 90s. And so you're going to see a very small range difference between here. But there's other things like daily range. What daily range means is the difference between the daily high and the daily low. So if you live near a body of water, a lot of times it cools off more at night. And so your daily range is going to be higher than if you lived elsewhere. So there's a pretty big difference between a house that cools off, let's say, to 75 degrees at night. At this point, you're not really exchanging a lot of heat. But if it cools off to 65 degrees at night, you actually start giving some heat back. And so it does make a difference as far as how much air conditioning you're going to need the next day. And then altitude does matter. The software will throw all these numbers in here, do all the math behind the scenes for you. Back in the day when we had to do manual J's or use the ACA speed sheet, which is what this is a screenshot of, we had to pay a lot more attention to this stuff. But the great thing about software is as long as you feed it the right information, it's going to feed you back the right information. So again, we go back to that rule. Heat travels from warm to less warm. It's 95 degrees outside and it's 75 inside. Heat is trying to come from outside to inside. And the bigger that temperature difference is, the more the heat will transfer. So let's talk about three ways that heat is transferred. Most of you already know this: conduction, convection, and radiation. Conduction is, well, you've probably done this before. You've been brazing a pipe. You forget that you've been brazing a pipe. Maybe the phone rings, you come back, you touch the pipe, maybe not even exactly where you were brazing, maybe a few inches uh, upstream or downstream of that, and you get burned. And why is that? Well, that's because that heat from the flame conducted through that pipe. And of course, copper is a great conductor of heat. But believe it or not, things like wood and even insulation do conduct heat to a certain amount. So that heat will get through that wall. So as we continue talking about walls, terms that you need to know is above grade walls, below grade walls, and partitions. So if we're looking at this house here, above grade exterior wall separates the conditioned space from the outside. And so these are considered exterior walls. So in this house, what would be an exterior wall? It would be these walls. Now, a partition is a different story. A partition separate the conditioned space from an unconditioned interior space, like a garage and an attic. So in this case, what would be a partition wall? It would be that green one. And partition walls have different rates of heat transfer because there are different temperatures on the other side of that wall. For example, when we're talking about exterior walls, it may be 95 degrees outside, 75 in, you got a 20-degree temperature difference. But what about this partition wall separating the attic? I'm sorry, the garage. Well, it's only 88 degrees in the garage, so we don't have as much heat that's transferring through this wall. What about the attic? Well, the attic can get up to 140 degrees, so there would actually be a lot more heat transferring through this portion of the wall than it would be an exterior wall. So we need to feed all that information into the software. Those are details that are important to enter in. So thermal conductivity is measured in a term called U value. And U value, a perfect conductor is a U value of 1.0. Obviously, the materials that we build a house are not made out of perfect conductors, so they're always going to be less than 1.0. They're going to be a decimal of 1.0. So let's think about a typical construction of the house, like the one that I built. I've got vinyl siding on the outside. I've got 7/16 OSB sheathing. I've got R15 insulation in the cavity of the walls. The frame is 2x4, 16 on center, and then we have half-inch gypsum drywall. But there's another part of the wall assembly that we sometimes forget, and those are air films. There's a thin film of air on the outside and the inside that acts like a little micro insulator. So when we think about a wall, we need to think about a wall or a ceiling or any material that makes up a house as an assembly. So even though there is R15 in this wall cavity, as we're going to see, that wall does not perform at R15. So each material that makes up a wall assembly has its own U value. What we're doing is trying to figure out what the average U value is for that wall, how quickly that heat travels from the outside to the inside through all those different materials. But you can't just add up U values. The way the math works, you have to first convert it to R values and then add them up. So how do we convert to an R value? You simply take your U value, and it's the inverse of it. So you just take 1 divided by your U value, and that equals your R value. And if you are looking for your U value, but you only have your R value, you do the same thing with that. You just take the inverse of the R. So those are just little fundamentals that you need to know. When you work with software, these are not details that you run into every day, but it's important for you as a practitioner to know how this stuff works. So again, let's take that wall assembly. We got our air films. And so if we know the R value, but the U value, if we need to know the R value, but we already know the U value, then we have to first convert to R. So then we can add all the R values for the total or the average R value of the wall. So let's take, for example, this wall here. We got 2x4 frame, R15, vinyl siding, half-inch gypsum. The outside air film, manual J determines that's an R value of 0.25. As we start going into siding, that's 0.61. And all this information is in manual J. You don't have to memorize this. When you're using software, you definitely don't have to know all this. You just need to make sure that you're putting in the correct materials into your software correctly. And this is what it's doing behind the scenes. So 2x4 wall, that's 16 on center. 25% of that wall typically is wood, and wood has around an R value of 2x4 of R3. The rest of that wall is insulation. So that would be 75% is whatever insulation value you have. In my house, it's R15. And so this is your R value of your gypsum. Of course, you have your inside air film. So your average R value is 11.62. Now we had R15 in this wall, but as you can see, this wall is not performing at R15. It's only performing at R11.6. And here's the U value. But this is all stuff that the Manual J software, like Quick Model 3D, is doing behind the scenes. If you need to check what the wall insulation value is in an existing home, go to an exterior wall, remove your electrical outlet cover, and then using a plastic, and I want to reiterate, a plastic crochet hook to see if there's any insulation there. You can pull on it, you can see what kind of insulation it is. And then you can also use some guides here. So pre-1972, not many houses had any insulation in the walls. In the 1980s, they started using R11. In the 90s, they started using R13. 2012 or later, we started seeing R15 and R19 mandated by code. So again, knowing what year the house is built and whether it had gone through a major renovation where they maybe gutted it and then insulated the walls while they gutted it, all that is important information. And the homeowner, if they've been in that house for any period of time, would know that. Measuring wall area. So again, in software like Quick Model 3D, you're drawing the walls. So, but you do need to know how to measure a wall with a tape measure, unless you're using an app like Cubicasa. So let's just take, for example, this floor plan here. We have a 30 by 60 building, 9-foot ceiling. What is the wall area? Well, you can start getting confused and thinking about, well, what's the floor plan area? None of that matters. What you got to do when you're measuring the wall area, or you're looking for like the running perimeter length of this building. So really that building looks like this. It's 60 feet by 30 feet by 60 feet by 30 feet. So you add all those together and you multiply that by the ceiling height. That's how you get the wall area. So don't get confused with trying to figure out what the square footage is. You don't need square footage to get your wall area. You just take your running length times your ceiling height, and you make sure that you measure to the outside of exterior walls. So sometimes when you're measuring room to room, you could get into the habit of measuring interior wall-to-wall lengths, but technically you're supposed to go to the exterior. And when you're measuring an interior wall, you would want to measure to the middle of it. Now, I'm here to tell you that this is not a huge deal to worry about. You want to be as accurate as possible, but whether or not this house was measured at 60 feet by 30 feet or 60 feet 6 inches by 30 feet 6 inches, that is not going to drive your load or your equipment size very much, unless you're dealing with a very large house. Partition walls. So this is the floor plan of my house. Remember that not all walls are exterior walls. This is a garage here, so this is going to be a partition. You're going to want to put in the software that's a partition. The software behind the scenes is figuring out what your running feet is, what your ceiling height is, and so it knows the difference in the wall area between a partition wall and an exterior wall. Let's switch over to windows now. Windows transmit heat. Again, we talk about the 3 ways that heat gets transmitted. Windows use 2 of them, conduction and radiation. Conduction happens through the frame of the window. So heat is just going through the frame of the window, same way it goes through a wall. And then radiant heat is kind of a cool thing to think about, because that is electromagnetic waves that come from the sun that react with anything with mass. So these electromagnetic waves travel through the void of space. They don't do hardly anything. They hit the Earth's atmosphere, they start moving molecules around, creating heat, but where they really start having a big effect is when they hit something solid with a lot of mass to it, like a window, like a building, like a person. So radiant heat is a big deal when it comes to windows. So another attribute of windows that you want to pay attention to is how many panes. Typically, an older home is going to have single pane windows. Most homes that are in the home stock that you're going to be running into, a typical neighborhood is going to be a double pane window. And then when you get into super high performance houses, you may see triple pane windows. Fixed or operable windows is another attribute that the software is going to ask you for. Also frame construction. So you're looking at what the frame is made out of. Sometimes you can't see that, but just know that older homes are going to probably have metal. Older cheap homes have metal windows. Then they started using metal with a thermal break. And what that means is that they separated the two sides of the window where the metal of the frame comes together with like a gasket that provides, doesn't allow the heat to just conduct right through the metal. Historic homes, older homes are going to a lot of times have wooden frame windows. Then PVC and vinyl. Most newer homes are going to have that. And then you may get into fiberglass windows frames with high performance homes. But the frame of the window, unless you're once you get away from metal and metal with thermal break, the characteristics of wood, PVC, and fiberglass aren't a lot. So don't feel like you need to get lost in the details here. Type of glass. Typically, we deal with clear and low E glass. So, low E glass reflects more radiant heat that allows it to pass through. A lot of times, low E glass will have a green tint. But one way you can find out is by holding like a lighter in front of that flame, and you're looking for the reflection. This is a double pane glass. And so what you're seeing is a reflection on both sides of each pane. So you have the one side and the other side of the pane that is closest to the flame. But notice how this side right here, you've got another double set of flames. Again, this is both sides of the outer pane of glass. But the one flame, flame number 3, is a lot darker. And that is the low E tint that is reacting with that reflection. And so that's what you're looking for. If you see one of these 4 flames that's a very different color than the other 3, typically that means you're dealing with low E. There's other windows like pane versus block glass. You're going to want to enter that in the software. A lot of times you'll see this block glass like in bathrooms because they allow light to come in, but they don't allow people from the outside to see in. And then reflective and tinted glass, they're out there also. Just be mindful of that. They have different attributes. You want to enter that correctly in the software. The building orientation affects how much heat affects that glass in cooling in summer. And so in the northern hemisphere, the sun is always to the south of us. Even when it's directly above us, it's slightly to the south. The closer we get to the equator, the less to the south it is. But what you got to remember is that the north side of the house never gets direct sunlight. And so again, knowing what the building orientation is important to enter in the software. East glass gets morning sun early in the morning, so that is going to warm up those rooms quicker than the rest of the house. West glass gets afternoon sun, so if you got west-facing glass, not only is it the hottest time of the day, but you're also getting blasted by the hot summer sun. Typically, those rooms heat up very quickly and can be troublesome. And then southern exposure glass gets sun most of the day. And so you sort of get this even amount of heat. But again, you don't want to take that for granted because southern exposure glass it's nonstop. It doesn't get a break. And so again, just knowing the orientation, putting that in the software, let the software handle the rest. Window shading is another attribute of windows that you want to understand because the sun is its effect on the window, and if that window is shaded or not, is things like latitude, time of year, the kind of overhang that we have, all that affects the sun's effect on the window. So say, for example, the sun in this position here, that window is going to get all the sunlight because it's not shaded. The sun is shining down on the house, and only this area right here is getting shaded. But what if that sun was higher? Well, then more of that glass would get shaded. And so knowing the latitude of the house, entering that in, again, when you put your climate conditions, your climate city into the software will automatically know what latitude it is. And so it's not like you have to do this by hand the way you used to when you did a manual J. So just another reason to use software. Make sure you're putting in the correct city that you're in, because that is going to affect your latitude. All right, let's take another attribute, horizontal overhang. So a lot of high performance houses have more of an overhang, and that provides a little bit more shading on the sun, sort of like a sun umbrella. So in this case, half the window is shaded because we have a better overhang. Another attribute is the vertical separation between the window and the overhang. So if this window was higher up in the wall, then more of it would be shaded. So you want to take those measurements to the best of your ability and to the extent possible be accurate. When you measure how big a window is, Manual J says to measure the rough opening. Well, that's really easy before the house gets finished. So this is my house. We've got a rough opening on the left, or the rough construction on the left, and then finished construction on the right. So typically when you do a Manual J on an existing house, this is what you're looking at, not this. But if you know what this looks like before it gets trimmed, you kind of know where to measure. And so you're not going to measure to the outside or the inside of the trim. It's usually somewhere in the middle. But again, if this window is 3 feet by 4 feet, or if it's 3 feet 3 inches by 4 feet 3 inches, that is not going to drive your load a whole bunch. So do not get hung up on these details. Just be as accurate as you can. Windows have a U value, and that U value is a lot lower than the rest of the wall. And we want to know what that U value is. The best way to do is to try to find the model number of that window on a tag that may be on the inside of it. And if it's not on one window, it may be on another window in that house. So just look around, and the best thing to do is try to find the model number of that window. And then you can look it up on the NFRC, which is National Fenestration Rating Council, I think, directory. You can get the information off that window. Maybe if the homeowner purchased windows recently, they're going to have one of these stickers, and so you can get it right off the sticker. If not, you might have to just use some rules of thumb for your area. But you're going to want to tell the software what the U factor and the solar heat gain coefficient is. And just make sure you're being methodical. Don't miss things like bay windows or their orientation. These windows do not face the same direction as that window. Also, transom windows, French doors, they're considered giant windows to Manual J. They're not considered like actual doors. Don't miss these windows here. When it comes to doors, here are the U values of typical doors. Like a hollow core door is 0.47, a solid core is a 0.39. You throw in a storm door, it provides some shading for that door so you get a little bit better performance. A lower U value usually means that it's going to be, it's not going to conduct heat as well, so it's going to have more resistance to heat transfer. But as you can see, these numbers aren't that far away from each other, so don't get hung up on what kind of door you have. There's probably only 2 or 3 doors in the house. It's not representing a huge portion of the area of the house. So be as accurate as you can, but do not get hung up on these details. The software is going to do a calculation, and it's going to figure out what your net wall area is compared to your gross wall area. Gross wall area would be like, if this is a 30-foot by 9-foot wall, your gross area would be 270. But then it's going to deduct windows and doors and other attributes. So in this case, it would deduct the window and door area, and the net area of the wall would be a lot less. So that's what the software is doing behind the scenes. If you're doing a Manual J or using the ACA speed sheets, you have to actually do this math yourself, and it becomes a huge pain. Let's talk about ceilings, because ceilings can let a lot of heat in during the summer. Ceiling under an attic or attic knee wall, so we all know about that. Usually it's a flat ceiling. Above it, you have a really hot attic. And then those attics can be vented, unvented, or encapsulated. So you're looking for vents like a ridge vent, a gable vent, a soffit vent, or if there's spray foam or another insulation on the roof deck, then that would be an encapsulated attic. Then you have things like ceiling on exposed beams. Well, above us is the roof. So where is the insulation in this case? Well, the insulation would have to be on the exterior. And so you'd want to know what that is. And sometimes that's hard to tell because it's covered by shingles. So sometimes you may have to make an assumption, and you just do the best you can. A ceiling below roof joists, or a cathedral ceiling. In this case, again, there's no attic here. The insulation is just in between the beams, so it would be up in these cavities here. So trying to figure out, are we talking about 2 by 10, 2 by 12 beams? The depth of the insulation is going to change. Ceiling insulation is usually measured per inch, and the type of insulation also matters. So you want to measure it. You want to know if you're dealing with cellulose or fiberglass. Some of those things do matter. Another thing to keep in mind is the amount of compression that happens with insulation, either because people have walked all over it or just over time, gravity just kind of compresses that insulation. It does detract from the R value. So say, for example, you've got R19 insulation that's been compressed 50%. It turns into R12. And so that can have an effect. Other things, just when you're out in the field, just be careful about vermiculite insulation. This was put in a long time ago. They found that it was a carcinogen. A lot of lawsuits happened. Most houses should have had this abated, but you may run into older houses that have insulation that looks like this. Maybe it's been covered over by additional insulation. If you see this, do not disturb it. Alert your homeowner immediately. And there are still ways to get that abated at no cost to the homeowner. This is a really important slide. This came from the Energy Vanguard, but it's the diminishing returns of insulation. The more insulation you pack in eventually has a diminishing effect. So as you can see here, the difference between R2 and R4 is pretty significant. And this is heat flow through a wall area, but the same thing applies in the ceiling. But as you start adding more insulation, notice how this curve flattens out. And so if you're measuring insulation and you're getting, if you don't know whether you've got R30 or R38, as you can see, there's not a lot of difference in heat flow. So do the best you can. Sometimes if insulation's been trampled on a little bit, you have to take an educated guess. But just know that don't worry about being too far off, because if you got it really, really wrong or really, really right, it's probably not going to make that much of a difference in heat flow. We measure a ceiling area. If it's a flat ceiling, it's usually the same as the floor area, which makes it a lot easier. So maybe you want to pull a Zillow or Realtor.com, figure out what the floor area of the house is. But if it's a vaulted ceiling, or a ceiling on roof beams, so you're not talking about a flat ceiling, you need to figure out what the area is, and you've got to figure out like the slope and what the C value is, and then you measure it by or you multiply it by the length. It gets really complicated, and that's where just drawing it on software like QuickModel makes it a lot easier, because QuickModel is figuring this out for you. So just another reason why you should not be doing manual J's or even using the ACA speed sheets at this point, because there is software out there. So give Russ your money, use the software, and let him do the heavy lifting for you. All right, floors. For example, if you're got a floor over this is a floor over an enclosed conditioned crawl space or a basement. Knowing if your basement walls have insulation or your crawl space walls have insulation or not makes a difference. If you're dealing with a slab on grade, we're not worried about the area of the floors. Rather, we're talking about the running length of it. So you would have to measure the perimeter, the running length of your house if it's slab. So for example, my house is on a slab, and I would have to measure this or enter this into the software, and it does the measurements for me. But just know that a slab, we're not talking about the area of the floor like you would almost any other floor type. When a slab, we're talking about perimeter or running length. So in this case, my house is 191 feet of running length for a slab. Infiltration, that is the air that enters a house through leaks in the envelope because of a pressure difference between outdoors and indoors. So common sources are things like wind. So when the wind blows really, really hard and your house is leaky, the wind blows right through your house and it carries heat with it. Stack effect, especially multi-story buildings, has like a chimney effect where heat rises in the winter. So you just have this natural pull. In the summer, it's reverse. Heat actually comes in through the attic naturally. Mechanically assisted depressurization. Let's say we had a big duct leak here, and so we're pulling in all of our return into our air handler, but we're leaking a lot of our supply air out. That will cause a pressure difference in the house, and we would drive more outside air into the house because the house is being depressurized. So that those kind of factors matter. So one way that we can measure infiltration, and just know that when we're measuring infiltration, it is sort of a wild guess. The more data that we collect, the more scientific that wild guess becomes, but it can still be a wild guess. So let's talk about quantitative. We're quantifying the infiltration. We have to use a blower door for this. So essentially a blower door depressurizes the house to negative 50 pascals, which is about zero point 0.2 inches of water column. And then that really accentuates the leaks in the house. And we start pulling in air. The blower is a calibrated blower and manometer, and it's measuring how much CFMs it takes to depressurize the home to 50 pascals. We plop that into a formula, as we can see here, that CFM 50. In this case, if it took 1,600 CFMs to depressurize our house to 50 pascals, that's called CFM 50. We put that here, we multiply it by 60, then we divide it by the cubic feet of the house. Well, how do we get cubic feet? We've got to take our area times our ceiling height. So let's say that our cubic feet is 14,760. We already measured our CFM 50. We put that into the formula. We arrive at a 65 ACH 50, or air changes per hour, at 50 pascals. The higher the number, the more your house leaks. And according to Manual J, they say that a house that has an ACH 50 of around 6.5 is considered average. But as you can see, there's a huge difference between average on the low end and average on the high end. The other way that you could do is just simply guess how leaky your house is. So there are a few maybe guidelines. You never want to use tight unless you can prove it with a blower door. So tight, and we're talking about 0 to 4.0 infiltration. You're talking about a high performance home. Typically, those homes are going to have a blower door associated with them. Use that blower door number. Even semi-tight, something like an Energy Star house, you still don't want to use that unless you have a blower door to prove it. An average house is something maybe that you don't have a blower door number on, but you know that somewhere in the 80s or nowhere, they usually fall within this range, but that still can be, there's a lot of exceptions here. You could have a house in the 80s that's pretty tight. You could have a house that was built last week that can be really, really loose. So again, we're just making assumptions at this point. When you get into semi-leaky in a house that's a little bit older, and then like a historic house, you can definitely count on that being leaky because they just didn't know back then how to seal a house. They didn't make any efforts, and those houses were incredibly leaky. So how much does it matter? This is my house. I took, in my Manual J software, I took it as being really, really tight, and then I took it as being really, really loose. I wanted to see, well, what would be the difference? As you can see, there's not a lot of difference here between really, really tight and really, really loose. But that is just my house. My house has a lot of other features on it that make it a high performance house. So the infiltration isn't a huge piece of the pie. Now let's take another house. This is actually a historic house, turn of the century house in Wilmington that I measured not too long ago. 3,200 square feet, 30,000 cubic feet, 3 level. And then again, I just changed it in my load calc software. If it was really loose, which it actually was, I came up to 7.3 ton. If that same house was built exactly the same, the only difference was it was super airtight, then it went down to 6.9 tons for the entire house. Not a huge difference. We're talking about half a ton difference here. Not a huge difference. The thing that you got to remember, though, is that there is loose and then there is loose. And like this house right here, I couldn't even get it to 50 pascals. So 11 ACH is actually too low of a number. I do not know what the ACH number of this house was because it was so loose, I couldn't even get it anywhere close to 50 pascals. There was no way to accurately interpolate that. And so this number could have been a lot higher than that. So just know that when you're dealing with super loose homes, again, just simply putting loose may not be loose enough. Internal loads. These are things like appliances in the house. They run, things like refrigerator have are constantly running. Maybe it's a house that has a lot of kids, so you're doing a lot of laundry. You would want to add some for the washer and dryer. If you see an aquarium, something again runs all the time, maybe adds a lot of moisture to the house, you would want to add that in there. If they're growing marijuana in the house, that's probably going to add a lot of moisture to the house. They probably, depend on what state you're in, they may or may not let you know about that, but you do want to be mindful of things that cause not only sensible but latent load. And that's why we're going to talk about sensible latent load, because these go into different columns in a manual J. Sensible load is dry heat. It makes a change in temperature only. Latent is hidden heat and moisture, and so it would make moisture changes, humidity changes in the house. So let's do a little quick exercise and see if we can figure out what kind of loads go in which column. So heat that conducts through walls and ceilings, would that be sensible or latent? What do you think? Well, it would be a sensible load. Radiant heat from windows and glass doors, sensible or latent? That would be radiant heat. Both of these are just conducting dry heat. There's no moisture involved. What about infiltration? Well, infiltration would be both sensible heat because it does carry a difference of temperature, but also latent heat because that air that flows through the house can contain moisture. Internal loads from people, would it be sensible or latent? It's actually both because we put out dry heat and moisture. And internal loads, how much internal loads from people do we put in a manual J? Well, people put out, according to manual J, about 230 BTUs per hour sensible and 200 latent. Per manual J, you would, if you want to know how many occupants are in the house, count your bedrooms plus one. But let's say you're doing a job for like a Mormon family that has like 12 kids. Just because it's a 4-bedroom house does not mean that you're just going to have 5 occupants. If you see that there is 12 occupants in the house, you put 12 occupants because that is the real world. All right, duct loads. These are affected by things like ambient temperature, what kind of insulation is on the ductwork, if the ductwork leaks. So you've got to pay attention to the ducts when you do a site visit. Things like duct surface area do have a minor effect because like high aspect ratio rectangular ducts that are maybe like really flat, they have more surface area, so technically they would conduct more heat than like round duct. But again, those are probably more minor, but you do want to pay attention to what kind of duct system because those are inputs into your manual J software that you're going to need to put in there and know. Just like a cooler, ducts that are leaky and not well insulated are going to allow a lot more heat to transfer than tight, well insulated ducts. Ventilation, knowing whether the house has an ERV or if they're just dumping in outside air into the return plenum of the unit, that matters. Or whether there's no ventilation. That is a line item on Manual J. Your software is going to ask you for it. You've got to know that answer. Blower heat. Technically, the wattage that's consumed by a blower motor is added as sensible heat to your load. But as you can see here, it's not much. It's 1,700 BTUs per hour. That's like, I don't know, a little bit more than a tenth of a ton. So if you remember it, great. If you forget it, probably not a big deal. There's a term called adequate exposure diversity, or AED. And what this does on a room-to-room load calculation, it tells you whether or not one portion of your house is going to heat up at a faster rate due to the position of the sun than the rest of the house. And that matters. So for example, here in the southern part of the house, as this sun tracks over the house, different portions of this house are going to get heated up. And the way that it does that is it takes your average glazing load, glazing is from glass, and it creates a line right here. And then it takes 30% more than that, and it gives you an upper limit. So it's the upper limit is always the green line plus 30%. Here is your 130%. And then this blue line would be your hourly glazing load. And what may happen is that this could have a spike in it and then kind of come back down to normal. And if you see a big spike that goes over 130%, then this portion of the house is going to heat up really fast, really quick. You may have some comfort problems for a portion of the day. So as we can see from my house, uh, I do get a little bit of a spike, but I don't quite get up to the 130%. And when does the spike happen? Well, it happens in the morning as the sun is coming up in the east. It hits the bay windows of my bedroom, but it's not really enough to create a problem. Plus, I have trees in my neighbors' yards that shade it. So in my house, it's not a big deal. But if you have like a lot of west facing or southern facing glass, you're going to see a spike in the middle of the day. And if that's the case, you may need to think about like a mini split to additionally cool that room or perhaps zoning. So again, we go to my house. What size unit did you think went in my house? We talked about this like an hour ago. Well, if my house was a high performance house, like to passive house standards, one ACH, R21 on the walls, exterior insulation, encapsulated attic, which I actually already have, R8 sealed ducts, and well, this should be a conditioned space. I would only be a wet 1.2 tons. But then that same house, if it was a really poorly performing house, like an older house that didn't have any insulations, really loose, ducts that were leaking, and vented attics, it would be 4.2 tons. So which number did you come up with? Probably somewhere in between. But did you come up with a ton and a half unit serving this house? Most likely not, especially if you're used to being in a southern climate and you haven't done a lot of heat load calculations. If you saw 1,600 square feet in Wilmington, North Carolina, maybe you thought somewhere around a 2.5 to 3 ton unit, but my house actually performs right around a ton and a half. So it just goes to show you that we need to do a heat load calculation, we cannot rely on assumptions. Now, I do want to say that after you've done thousands of load calculations like I've done, and you've been sort of in the same climate for your entire career, you can start seeing patterns and you start seeing the same house over and over again. And you start understanding what things drive a load and what things don't really drive a load. And I got to the point where I could take a look at a house and say, okay, this is a 1,800 square foot ranch house in my old market of Greensboro, North Carolina, built in the 80s. And I just knew that a 2.5 ton unit was going to serve that house just fine. But you don't get to make those assumptions until you've done hundreds and thousands of heat load calculations like I have. So please do not take this as it's okay just to assume what your load is, but eventually you will start seeing patterns. Well, at this point, we're going to join Russ's explanation of Quick Model 3D that's already in progress from the original class that took place a few days ago. And then from this point on, the recording will be the recording that took place a few days ago. So keep watching. And again, thanks for signing up for this class. I really appreciate it.
Innovations.
Sorry, Russ,
So
forgot to start
you just
recording there.
no problem. No problem. And so I set the ceiling heights at 9 feet. So that would be your plate height. There's a way to do vaulted ceilings. I'll show you how to do that really quick. But basically you hold down the Alt key and you hit click. Oh, let me get in the right tab here. And it places a box. Okay. And then you just drag that box and you get it to line up with the rooms like this. And if you got another little box there, you just place another box like so, line it up to the walls. Oops. Like so. And then you group those two boxes together by holding the shift key and this group button, and now they stick together. So when you drag it around, they're stuck together like that. Okay. So then you just go around the house and you just build the house out of boxes, and it goes really fast once you get used to it. And some things you can ignore. You don't have to be super detailed on a lot of this stuff. Tim kept mentioning understand what's important and what's not important, so you can save time. I have a saying I use all the time, and it's better to be approximately right than to be precisely wrong. And so what that means is it's just do your best, just go for it. But what really helps is after I do a load calculation, I'll show you. It really helps a lot as you're doing these. Do a house, and then just take a few extra minutes and sit down, copy and paste the loads, save them off to the side, and then make one change to the house. And then run the load calcs and compare that to your previous load calcs. And then do that for each different kind of measure. Do it for the windows, do it for the infiltration, do it for the wall R value. And what happens, you'll start learning what's important and what's not important. And you'll start realizing, I don't need to be super precise on this stuff. Okay. And by comparing before and after loads really helps a lot. So you can see I'm placing these boxes. And but what I'm actually doing is each box I place creates 6 surfaces. It creates 4 walls, a ceiling, and a floor. And then it's tabulating all that information in a table. And I'll show you that really quick. Let me just get a few more boxes in here. Okay, so I just filled that in with boxes, but what I'm actually doing is I'm creating rooms like this. So you see how it's doing those rooms, and each one of these rooms has exposed walls. When these little boxes touch each other, you see how they collide. It now knows that it can ignore the wall between those 2 boxes because that's what we call an adiabatic surface. There's no heat transfer through there. And then if I group these 2 together, like so, and they become one unit, they move around together. Now it's considering that a room, and so it's going to do the loads on that room by itself. Okay, so let me open a different file here real quick. Oh, and then the other thing, after you get it built, then you can place windows on here. Really simple. You can just say 2640, and it'll just place windows. You can put the sizes in. You can copy the windows and place them. You can place doors and all that other stuff. So it's really easy to build the house. Let me show you real quick how to do a vaulted ceiling. So we've got all these different rooms. The basic room is called a rectangle room, but we have a whole bunch of other kinds of rooms and boxes that you can use to build a house depending on the complexity of the house. But a basic vaulted ceiling just looks like this. You just put it up there. The tab key rotates it to whatever direction you want it to face. The green handle will change the height of it, like so. And there, that room now has a vaulted ceiling. Or it could be a double vaulted ceiling. It could be something like this. Oops. There's a weird handle issue going on right now. Something like that. So now it's a double vaulted ceiling, and you can arrange that to make it look accurate. Okay. All right. Let me open up a file that actually has the house fully built. It'll take a second to load. One of the things it has to do is it has to look at all the touching walls and make sure that those are all calculated correctly. There's a lot of math going on in the background. You don't need a super fast computer to do this. You want about 8 RAM or gigs of RAM, whatever it is. You don't have. My computer is it's a $350 gamer laptop that I bought about 4 years ago, and it works fine. And I intentionally use kind of an old computer because I don't want our software to have to require a really nice computer. So it does get a little slow at times. Let me delete this air handler really quick. So here's his house all built. And if you look closely, I can darken the rooms here so you can see them a little better. You can see there's some vaulted ceilings in some of those rooms. Okay, I've got all the windows in. It's got this little bay window back here. I did the garage, and I've indicated that the garage is unconditioned space, and that's why it's blue. Okay. So this house is basically all built and ready to go. I can build a house like this in probably 15 minutes with a set of plans. Okay. Then the next thing it wants to know is how many systems are on this house, and you do that by placing air handlers. And I'll just place an air handler right there. It by default it places a horizontal air handler because that tends to be the most common. But you can change that to be an upflow. You can change it to be a downflow. We've got little We've got little mini splits you can put in there. You can place a little mini split, a little ducted mini split. We've got little ductless mini splits you can place. You can put those around the house and stuff like that too. So a lot of different ways to do it. Let me go back to horizontal. Okay. Now, if you place more than one system in this house, you have to assign rooms to that system. There'll be a drop down list of all the rooms. So as I'm building this house, it's tabulating all the areas. So all the windows that I placed, here's all the windows that I put in this house. If I zoom back a little bit, if I click on the table, you can see which window it is. It's this one here. If I click on a window, it'll highlight it in the table, and you can see which window it's going to be this one here. Okay. So Tim mentioned the types of windows. There's lots of types. If you click this down there, it'll list all these different types of windows. All of these types come from this place up here called libraries. All right. Libraries is where you store all your different window types, door types, wall types, and these are totally editable. All right. So here's what the software comes with is all these windows. But if you want to change one of these, you can edit it. If you want to add to it, you can do all kinds of different stuff and changes. You can export these and import them back in later. So the libraries are really useful, really easy to customize. Okay, so I got the house built. Let me show you. Here's all the windows. Here's all the walls in this house. Look how many walls. This is why you don't want to do this by hand because there's 36 walls in this house. Why are there so many walls? Well, because it's keeping track of them on a room by room basis. It's looking at each individual wall. Plus, look up here. You've got knee walls. All right. You've got, oops, go to the back, left side. When you've got these little bay windows, each one of these is a separate wall. That's a wall. So it's keeping track of all those because of how you built the house. And as long as you built the house reasonably well, it'll keep track of everything for you. You want to make sure you set your wall heights early on. I've built a house and then realized I didn't have all the wall heights set, so I had to go in and actually raise each room individually. So I click on, had to raise the room up, click like that. But you can do it. It's just a lot easier if you set it at the beginning. Okay, so this is pretty much ready to go at this point. In the data tab is where you set all your types. So this house was a 2x4 wood studs with R15 rigid insulation on the outside. So that's the type that was set. Slow computer is taking its time. And no. Tab. So here's all the walls. I could change individual walls if I want to, or I can change them all at once. This has all slab on grade floors. So it's calculating the perimeter of all the floors for you. So all that geometric takeoffs that you would have to do to a set of plans is done for you simply by building this little 3D model of the house. Okay. All right. So at this point, we're pretty much ready to go. I'm going to go ahead and I'm going to click the Energy Gauge Loads button. We partnered with a company called the Florida Solar Energy Center. They have a software called Energy Gauge that is approved for ACA Manual J. And they've basically loaned us their Manual J module. And in exchange, we've loaned them our 3D front end to use on their energy modeling software. And so here's Energy Gauge. It comes with our software. It's a single license. You'll see it says Energy Gauge here. You'll notice that it looks very different than Quick Model. That's because it is a different software, but it talks to Quick Model. Quick Model sends all that geometry, all those window types, all that other stuff is being sent to Manual J. It wants to know, here's where you just, you set your climate location. So you pick a state, you pick a city, it automatically fills all this stuff in. You can edit these if the city that you're in is not on the list. You can edit these and save them, okay? But I really discourage you from messing around with the outdoor design temperatures. A lot of people will see the outdoor design temperature for their city, and they'll say, oh, wait, that's not hot enough. It gets a lot hotter than that. But you should not do that. All right. There's a lot of reasons for not doing it. And one of the main reasons is that when you say, it hit 105 degrees last year, and when you say that, what you meant is that was the maximum temperature of that day, and it was only that temperature for a very, very short period of time. Houses have thermal mass. Houses have insulated. They don't see that same peak that we do when we're standing outside. They experience temperature very different than what we do. In order for a house to experience a certain temperature, it has to be at that temperature for a long period of time, like a couple hours. Okay. And so it never really sees those super high temperatures the way we do. It asks for a couple little bits of information about the cooling system, like what kind of is it. On the ducts, it asks what the R value is. That's where you enter the R value of the ducts, where are they located. There's a lot of different ways to measure duct leakage. You can actually test it. You can enter it. If you do a duct leakage test, you can enter that number. Or out here in California, we quantify duct leakage as a percent of total airflow. So you can just plug that number into it. So it just wants to know all that stuff, and you assign it to its system and all that stuff. And it's pretty straightforward. Then it'll ask for some heating system, some mechanical ventilation system. You enter a mechanical ventilation system. And then for air leakage and infiltration, kind of like the ducts, there's a lot of different ways to enter infiltration. If you do an actual blower door test, you can enter your CFM50 number into this house. But we tend to use ACH 50 as sort of a target for new construction. But however you want to do it, you can do it there. Or you can use the Manual J defaults. If you click here, you'll get those choices that Tim talked about earlier: tight, semi-tight, average, semi-loose, and loose. Okay. But if you enter a number down here in air leakage, you want to click that and tell it that's what you want to use. Okay. And then that's pretty it. It does the AED, the automatic exposure diversity for you. And that's pretty much it. Then you click this magic calculate Manual J8 button here, and it will do your load calcs for you. And there they are. So your winter is 23,388, and the summer sensible is 14,000, and the Layton is 1,900 for a total of about close to 17,000. Now, what I was saying before is you see all these individual numbers here. It'll show window, wall, ceiling, door, floors, infiltration. These are what change. When you change the R value of the walls, that number is going to change, and that number is going to change. But it's not going to change. That's a small percent of the total load, and that number is only going to change by a small percent. And so there's this pie chart thing here that you can look at, and this is always really interesting to me. You'll notice that on heating, slab floors lose a lot of heat through the slab edge. It's amazing how much heat slab floors lose, but they have very low gains in the summertime. Slab floors are great for summers, but they're terrible for winters. You can see here the walls are only 21% of the total load and of the total heating load. So if you if you're not sure whether the house has R11 or R13 in the walls, try both of them and see how much it changes here. And what you'll see is it'll only make like a 2% difference in the total load. And it's just not that big of a deal. It's not that worth worrying about, because remember what we're trying to do is we're trying to get this house to fit in a bucket. And that bucket is the size of equipment that we want to use. And these buckets are big. We've got 2.5, 3.5 tons. And we're trying to fit these houses in these buckets. It doesn't matter if the house size changes by a little bit when your bucket's this big, okay? So it's not that big of a deal. Get used to it, though. Understand the difference. Be able to look at one of these and go, whoa, wait a second. That internal gains looks like it's way too much, okay? In this case, it's not. That's about what it typically is. But get used to understanding, and that just comes with practice, okay? So, once all your load calcs are done, what I typically do is I'll take a screenshot of this, and then I'll go back into QuickModel and I'll make some changes, and then I'll come back here and look at it and just see how big of a difference it makes until I'm kind of satisfied with those numbers. And then you go to Manual S and you start picking your equipment. So there you go. That's Manual J. That's the short version. Any questions?
That's awesome. We'll probably have to hold the questions to the end of the class just so we can keep rolling. But keep an eye on the chat, Russ. There's a few questions that came in there while we're on break and while I'm doing the manual S portion. Feel free to answer those questions. We're going to take 5 minutes, just enough for me to get up and pee, and then we're going to come back because we've got a lot to cover still. But hang in there, and we're going to get into manual S also. There is one other thing I just wanted to share. Could I get my screen? Share
Oh,
my
sure.
screen, Russ? Yeah.
Yep.
Yeah. I don't know how this slide got deleted, but I did want to share this with y'all. Diminishing
And by the
return.
way,
Oh, go ahead.
Tim, I won't need a whole lot of time on the manual S because there's
Okay.
not a whole lot in the
Yeah.
software that
Okay.
you just tell it. You basically tell it the
Okay.
equipment. So,
Okay. Diminishing returns of insulation. This is one of those other things, again, being pragmatic. I'm just going to credit Energy Vanguard. I stole this screenshot from Allison's blog, but it's just really awesome. And this applies not only to wall area, it's the ceilings also. There's a big difference between R0 and R2 and R0 and R6. But once you get down over here past R22, it starts flattening out a lot. And so if you measure that insulation and you don't know whether it's 50% compacted or 75% compacted, y'all, once you get above a few inches of insulation, there is not a lot of difference here. So again, don't worry yourself sick over um, what what that is, because as long as you have insulation, that is almost half the battle right there. And then whether or not it's R20 or I'm sorry, R30 or R38, we're not talking about a lot of BTUs. Okay, let's take a 5 minute break. We'll come back and we'll get started with manual S. All right, we're gonna go ahead and get started. And I just want to let you guys know I realized about halfway through Russ's presentation that I never hit the record button. So what I'm going to have to do on my own time is go back and record myself doing the whole Manual J presentation for the recording. So what that means is that you're probably not going to get this tomorrow because I have to go out of town starting tomorrow morning. I'll have to work on this on Monday. So just keep that in mind. You'll get the recording. I just have to go back and redo this all over again. The good news is I'm really going to learn Manual J really well. All right, let's share the screen. After you've done the Manual J, the next step, I assume everybody can see next steps right here. We're good? Okay, thank you. Is Manual S, where we need to determine what the required airflow for the system that we selected. And we also need to match our sensible, latent, and heating capacities to what the loads are. And then later on, we'll build a duct system with Manual D. So that's, again, the ACA design process. Manual S equipment selection. We all know what danger it is to oversize a piece of equipment. We cannot control our humidity in the summer when that happens. We have poor comfort control because your unit is turning on, it's turning off, it's blasting you with heat or with cold air, then it's not. And then that short cycling reduces equipment life and it wastes energy. And so oversizing means that our capacity is way higher than our load. Undersizing, the only problem with that is that we have poor comfort control. The system can't keep up on a hot or cold day. And so if we have not a lot of capacity and too much load, if I had to pick between the two, I always pick undersizing because at least when I undersize the system, I'm not likely to grow mushrooms in the house and mold and all kinds of stuff. But the purpose of Manual S is to right size, which means we're selecting it within tolerance that it gives us. And we also want to do something called sizing aggressively, which means if we have to pick between two size units, we're going to usually opt to the smaller size because Manual J even tells you that they have inherent, it's not like, it's not overkill, but it's a range. And Manual J has some not safety factor, but sort of safety factor built into it. You guys kind of know, I can't remember what exactly they called it, but essentially your Manual J sometimes can be a little bit overinflated, especially on the heating side. So Manual S uses something called a sizing factor, and it indicates how under or oversized the equipment is. So for example, the sizing factor, all we do is we take our capacity and we divide it by load. So for example, if our capacity is 24,000, our load is only 19, we are 1.26 sizing factor or 126% oversized. Well, is that too much oversized? Well, Manual S gives us some guidelines for that. But the thing is, we start off with a Manual J load, and we don't always know what kind of equipment we're going to be putting in there when we get the load. So wouldn't it be nice if we just could apply our sizing factor to our load and get what Manual S calls a sizing limit? This is like the biggest unit we could put in. That means we take our load times our sizing factor. And if our unit capacity is bigger than this number, then it's too big. So let's take an easy one, gas furnaces. Let's say, for example, this applies to single stage, multi-stage, and modulating burner. Minimum heating size factor is 1.0. That means that they want you to have at least enough heat output out of your furnace than what your heat load is, right? That makes sense. If you need a bunch of heat, then you need to be able to produce a bunch of heat. Then it gives us some guidelines here. If your heating load is really, really small, 25,000 BTUs or less, or perhaps the correct furnace for your heating load doesn't have a blower that's capable of moving the air that you need it for air conditioning, then you're allowed to oversize this up to 200%. And finally, if you're up in high elevations, your minimum size, you're going to start out at 1.25 because being in a high elevation, it derates your furnace. So you're allowed to have a bigger furnace. Okay, so let's take an example. Here's our load. Sample load is 43,000 BTUs. You may also see it written like this in MBH, same thing. And here's what furnace we think we'd like to put in. We got single stage 80,000 BTU input. It's 96%. So it's going to be putting out 76.8 MBH. So here's our capacity. Here's our load. Is this going to be compliant? Well, what this is saying is that we're allowed to be 100 to 140% oversized, but no more than 140% oversized. So we take our load times our size factor. So what's the maximum sizing limit we could have for this unit? 43,000 times 1.4. The maximum output of our furnace can be 60.2 MBH. We've got a 76 one. So that's going to be too much. Technically, this furnace does not qualify for manual S. So we'd have to go with the next size furnace down if we could, as long as it could move the air that we need for air conditioning. We have what we call standard sizing limits. This is for air conditioning and heat pumps. And I'm trying to simplify this. This may not be completely 100% accurate, but manual S creates a bunch of rules, and I'm trying to put these rules into buckets. And so the bucket that I'm putting this one in is if you're sizing an air conditioner or a heat pump in a cooling dominant climate or maybe a balanced climate. So a southern climate, maybe mid-Atlantic, something like that, then you can use a standard sizing limit. And so they give you some rules here. For example, if you have single speed equipment, if your load is less than 24,000 BTUs, then you use those rules. If you're over 24,000, use those rules. And if you have two-speed units, then you use those rules. So let's take a sample load. Our load is 23,000 MBH, and out of that, 18 of it's sensible and 5 of it's latent. Here's our equipment. We've got a 24 MBH total. Out of that, 20 is sensible, 4 is latent. So which rule are we going to go by? These, because we're under 24,000 BTUs. And so what it's doing is giving us a range. Our total cooling should be 90 to 120% of our load. Our sensible cooling, we're actually allowed to be a little bit undersized. We're allowed to be 90% of our load. But our latent, we need to be at least 100% of our latent load, because latent load is moisture. And so let's see if this piece of equipment falls within those guidelines. We got to take the maximum 1.2, because obviously our unit is bigger than our load, so we'd be more looking at the 1.2. And so what's the most capacity that we're allowed to have? Total capacity is 27.6. Well, we've got 24, so we're good. Because we have more sensible than load, sensible capacity than load, we know that we're compliant here because we're at least 90% of it. But then the main thing we got to keep in mind is, are we meeting our latent load? And in this case, we are not. So we are not compliant with manual S because we're not meeting our latent load. Let's take another example. Again, we're in a cooling dominant balanced climate. This time we've got a load that's over 25,000 MBH. So which one of these rules we're going to go by? We're going to go by this one. In this case, everything looks pretty similar, only that total capacity tends to tighten up to 115% instead of 120. Well, let's see if we're compliant here. If we take our load by 1 and multiply it by 1.15, this is the maximum AC total capacity we're allowed to have. We are barely over it. So according to Manual S, we can't use this equipment. But I'm going to tell you, I do not pay a lot of attention to total BTUs. I am more worried about having enough, but not too much sensible, and definitely having enough latent. So if I'm close here, I am going to keep moving forward to see whether the rest of this matchup qualifies. Well, obviously, we are going to be more than 90% because our sensible capacity is more than our load, but just by a little bit. 2,000 BTUs, that's not a lot. And then our latent capacity is well over 100% of our load. So really, in this case, I would not feel uncomfortable putting this system in a house, even though technically, because of the total BTUs not matching, it would not comply. We're still good. All right. Why is my screen freezing up? All right, now, next thing. We got two-stage piece of equipment now. Let's see how that matches up. Here are our rules. It's actually the same as the ones that we just did. So we take our load, multiply it by 1.2. This is the biggest unit we could put in total. We're under that, so we're good. Our capacity is a little bit over our load, so that's good. We're at least 90% of that. And our latent capacity is more than our latent load, so we're at least 100%. So we are good there if this is a heat pump. And one other thing we want to talk about is supplemental heat with the heat pump. We should use supplemental heat only as required when the heat pump capacity is insufficient to meet the heating load. But in this case, we're more talking about cooling. Now let's talk about heating dominant climates. And Manual S has got what they call advanced sizing limits. And so there's a little bit more rules that get applied here, and it gets pretty convoluted very quick. And so again, we're trying to be pragmatic. So let's try to put some of these rules in some buckets. First thing to understand is that when you're in a heating dominant climate where your heating load vastly outweighs your cooling load, or maybe it's just your heating months, how many months you're heating versus how many months you're cooling, are really imbalanced. Typically, single stage heat pumps are not going to work, and we're going to show you why. You're allowed to maybe try out a two-stage heat pump, but we're also going to see how that's pretty challenging also. So let's take a two-stage heat pump and a sample load. Our total cooling load is 25 and our total heating is 45. Let's say we tried out a 4-ton heat pump. So the reason why we thought it was a 4-ton heat pump, because we had 45 MBH of load. Well, actually, that heat pump down in the whatever design conditions that it's running at, it only puts out 38, which means we have a shortfall of 7, which we're going to have to make up with supplemental heat. But here's where it really gets bad. You've got 48 MBH of coolant and only 25 of load. And so what does the rule say? Well, the heat pump sizing factor cannot exceed 1.2. Well, we're not even at 1.0, so that's fine. But our cooling capacity cannot exceed 1.3. And so when we do that, the maximum total capacity we're allowed to have is 32.5. We're all the way up at 48. This is definitely not in compliance with Manual S because we're way oversized in our cooling. So maybe we decide, all right, well, let me try a slightly smaller heat pump. Maybe let's go down to a 3-ton, and because we're so vastly oversized with cooling. Well, let's do that. Now, all of a sudden, our heating capacity is way under our heating load, so we're going to need a lot of supplemental heat, and our customer's not going to like his energy bills. And even then, even if we go down a full ton, are we still compliant here with cooling? Well, when we click through some of this, when we do the math, again, the maximum is 32.5, we're still over. And they're going to hate us because they're going to be running a lot of supplemental heat in the wintertime. So these are kind of based on real numbers. What you're going to find is in some climates, heating dominant climates, not even a two-stage heat pump is going to be good enough. So that leads us to variable speed heat pumps in heating dominant climates because they have the ability to do what we call turn down. They can run at a part load capacity a lot better than two-stage. And the cold climate heat pumps really have the ability to turn themselves down. And actually, in the wintertime, they can run almost like a turbo speed on really cold weather for a little while if they need to. So here are some of our advanced sizing limits per Manual S. Our latent load, or latent cooling factor, essentially we have to meet our latent load. We always have to meet our latent load, okay, because latent is moisture, and if we don't meet our latent load, that gets dangerous. The heating size factor should be greater than or equal to 1, so we need to be able to heat the home. We need to meet our heating load. And then they start talking about minimum compressor heating capacity, and there's also minimum compressor cooling capacity. And so it gets kind of convoluted here. I'm trying to keep this simple, and I may not be explaining this exactly how I should, but here's how we need to think about it. We've got a load here of 25 cooling. This is what our load looks like, and here's what our 4-ton capacity looks like. Now, this is a better heat pump, but let's see whether this complies with Manual S. All right, trying to click through everything. Here's our heating load. Here's our heating capacity, 45 load, 48 capacity. We exceed that. So we're actually going to be able to meet that heating demand without using any supplemental heat. That's a good thing. All right, but then the question is, can we meet our latent load? Well, let me go back. Well, when it's running at full capacity, yes, we can. But the problem is that it's never going to run full capacity because our summers are not as extreme as our winters. And so we're going to end up having to look at the minimum capacity numbers of this heat pump. And when we look at that, all of a sudden our latent capacity does not meet our latent load, and we're not in compliance. So what do we do? Well, the only thing we can do when our latent capacity doesn't meet our latent load, and we've tried everything else, and we got a heat pump that works in wintertime, and we're in a heating dominant climate anyway. We've only got 2 months of summer and just a couple of months of shoulder season, is we need to add some supplemental dehumidification. That's really the only choice we have. And just when we are starting to convert gas furnaces and ACs over to heat pumps, we're going to have to put in a larger tonnage heat pump than the AC unit that we took out. And the flip side of that is that AC, when that heat pump goes in AC mode, it may not be able to turn down to the point where it can remove the latent load. In that case, dehumidifiers start to become our reality. And that's just the best I can do with explaining the situation with cold climate heat pumps and manual S and their attempts to address that. Let's talk about supplemental and emergency heat, strip heat. All right, we got a load of 45,000 BTUs. Our capacity is only 30,000. This happens a lot in moderate climates, even here in North Carolina. I've got more heating load than I do cooling load. You guys just saw the numbers there. And so I'm going to size my heat pump for my cooling because I've got 8 months out of the year is cooling and only 2 months is heating. So, of course, I am going to have a shortfall in heating when I compare the capacity of my heat pump in my design temperatures compared to my load. So what do I have to do? Well, I got to add some supplemental heat. And I have some guidelines here. 1 kW equals 3,400 BTUs, and then I have some other kW, typical kW sizes. So what would I do here? Well, I would probably add 15,000. This is what I need. I need an extra 15 in order to meet my 45. Well, 5 kW gives me 17. So, okay, I'm going to overshoot a little bit, but it's not going to be that bad. And so I'm going to put 5 kW for supplemental heat. But emergency heat is a different story. We only need what's needed in supplemental heat. But according to Manual S, emergency heat, here's how they want us to think about it. They are not trying to heat the entire home to 70 degrees on the coldest day of the winter with emergency heat. They are only trying to keep the pipes from freezing and trying to keep grandma from dying from exposure. All right. So really the emergency heat load is, they're telling us 85% of what our actual load is. That's the kind of load that we're trying to control. So we're probably not going to heat that house to 70 degrees if the heat pump happens to fail on a really, really cold design night. But we're going to be able to maintain it somewhere in the 60s. All right, and so what size heat strips would we size of that load? Well, here's what we need. And they're telling us we can be anywhere from 95% to 175% of the emergency heating load. So we could actually put some pretty big heat strips in here if we wanted to. Here's what we could do. If you had 10 kW of emergency heat, you'd have it right here ready to go. This kind of gets pretty close to your emergency heat load. But then if you already had 5 kW and you were able to separate these and stage them, then you'd still have the 5 kW as like your second stage of heat, and you could throw both stages on there and actually be able to heat the house. So that's one option. But I would be okay in this situation with either having 10 kW of heat or 10 kW plus another 5 kW. Either way, if you stage it, your heat pump is only going to use what it needs. I mean, the worst thing that's going to happen is it's going to cycle off. Big deal. So don't get wrapped up into trying to figure out what the exact kW you need, because you only have a few choices that you can pick out from the supply house anyway. Variable speed heat pumps that meet 100% of the heating load, according to Manual S, are not required to have supplemental heat or emergency heat. And I thought that was kind of weird. It says it's not required. And maybe, Russ, when you present, maybe if you want to provide clarification on that, emergency heat for variable speed heat pumps. But, essentially in a cold climate, you want to try for the heat pump to meet all of your heating load anyway, because you're going to get a lot of cold nights. And if you're running heat strips every night, customer's going to hate you. Two terms we need to understand: sensible heat ratio and sensible heat factor. Sensible heat ratio is when we're talking about the load. All it is we're dividing our load by, I'm sorry, sensible into our total. Let me say that one more time. We're dividing our sensible load by our total load. So sensible heat ratio is essentially telling us what percentage of our load is sensible load. Okay? Or another way to think about it is if we know what our total load is and we know what our sensible heat ratio is, we just multiply them and we get our sensible load. But it's just a percentage. So in this case, if our total load is 24 and our sensible heat ratio is 0.85, that means 85% of this 24,000 BTU load is going to be sensible. Okay, so that's what our actual sensible load is going to be. We just multiply them. And that means that anything that's left is latent. And so in this case, 3.6 is latent. Same thing with sensible heat factor. It's the same thing, only it's talking about equipment capacity. And I will tell you that some manufacturers and some people actually use sensible ratio for both. That's what makes it kind of confusing. But technically, sensible heat factor is used for referencing the equipment. Same thing. The same math, instead of load, we're just dealing with capacity. It's just a percentage of what our capacity is sensible compared to the total. Okay, so if we had total capacity was 23 and our sensible heat factor was 0.8, that means our capacity, sensible capacity, 18.4. That means that the latent is the rest, and we have 4.6 MBH of latent. So what you're trying to do is compare your load to your capacity, and you're trying to get these to match as closely as possible. All right, here are a few guidelines about understanding sensible heat ratio. If we're under 0.75, that means that 25% or less of our heat load is sensible. That only means that the rest is latent. And so the lower our sensible is, the more our latent is. So if I saw a load that was under 0.75, I would, especially nowadays with modern construction, I would think, okay, we got a high latent load. Maybe we're in a humid climate, maybe our envelope leaks, maybe the house is ventilating a lot. Maybe they got a lot of aquariums. Maybe they're growing a lot of marijuana in it. We don't know. But if we see a sensible heat ratio of under 0.75, there's a lot of latent load. And that, to me, kind of flips a light on that says, okay, I got to make sure I meet that latent load. If we see it between 0.7 and 0.75 and 0.85, that's pretty normal. Most climates, most loads. When we get above 0.85, we're dealing with either dry climates or a high performance home, a newer home that's not leaky, that maybe has an ERV and it's controlling its moisture. If you're seeing sensible heat factor, if you see a unit that has under 0.75, this thing is an absolute beast at dehumidification. And that's what the old 12 and 13 SEER R22 units did, because they didn't care about efficiency as much. And they could run a cold coil, and they could run sensible heat factors of under 0.75 all day long. The only problem was it wasn't that energy efficient. And then they started increasing the SEER rating requirements, and these units can no longer run that low of a sensible heat factor. So most mid-efficiency equipment today, when you look at the specs, you're going to see it in this range, 0.75 to 0.85. But your higher SEER variable speed equipment, you're going to start seeing them in 0.85 all the way over 0.9. You're going to see, I mean, some of these units, I've even seen a 1.0 sensible heat factor, which means that it removes zero moisture according to the specs. Now, whether it actually pulls out a couple of drops every now and then, we don't really know. But according to the specs, the higher that sensible heat factor is, the less moisture it's removing. So you could have a situation where you've got a older leaky home and you've got a sensible heat ratio of under 0.75. And you go and you sell them a brand new variable speed unit, high SEER, 22 SEER, and it's over 0.85. And all of a sudden they're calling you in the middle of June and they're saying that their unit that their house is really, really humid. And their old unit didn't used to do this, but that really expensive unit that you sang the praises on cannot control humidity. And this is why, because you put that unit that can't remove a lot of moisture into a load that has a lot of moisture. And so you've got to really be careful about that kind of stuff. That's why we have manual S, because it's showing us, giving us guidelines to avoid those situations. Other thing to realize is that per manual S, if you have excess latent capacity, so let's say it's the other way around, you've got way more latent capacity, you have latent load, you can take 50% of that excess latent capacity and you can apply it towards the load. So if you're a little bit undersized on sensible, that kind of gives you a little bit more sensible capacity, gives you a little more peace of mind that you're not going to have comfort problems. So let's take an example here, and I think I just realized my math may be a little bit wrong, but let's say somebody is unmuted. Let's get you muted back here. Okay. Let's say the here's your load, 30 total, 25 sensible, 5 latent. Here's your capacity, 30 total, only 23 sensible, so we're under the 25. We may not actually reach our thermostat set point on a hot day, but we got excess latent. What this is saying is that we can take this excess latent and we can apply it towards a sensible capacity. Here's where my math is wrong, because it should be 50% of the excess, not 100% of the excess, but essentially we can take half of this, the excess, half of the 3.5, and apply it towards our sensible. And so we'll actually be really, really close to our sensible load. So it gives us just a little bit of confidence that we're going to be okay on a hot day. It's a lot of rules, right? So here are my simple rules. Again, if you're going to take any screenshots, this is probably my simple rules, probably my most controversial rules. Like, I will probably never let Ed Jonawak see this slide because he'll probably never talk to me again. But here's how I think about it. And Russ, if I'm wrong, please by all means correct me when it's your go. For cooling dominant and balanced loads, sensible cooling, just don't give it any more than what's needed. Start with a smaller unit, see if it'll work. Slightly under is okay with sensible cooling. Latent cooling capacity, have enough capacity. You've got to meet your latent capacity. Just remember 50% of the excess latent, if you have any, can be applied towards sensible. Total cooling, if you do your sensible and your latent right, your total will take care of itself. Gas heat, have enough. Just make sure you have enough. No more than what you need, but just have enough. Heat pump heating size. Again, this is a cooling dominant or maybe a balanced load. Size it for cooling, and you just use a little bit of supplemental heat for the rest. Because remember, manual J kind of overinflates your heating load anyway. So, for example, my strip heat never runs on my unit, and it's just my heating load says it should, and they never came on a design day. So just keep that in mind. Supplemental heat, we just add that to the heat pump heat. We only need what's needed so that we can have enough heat. We don't need to overdo our supplemental heat. But emergency heat, if it's a different heat strips, then stage it if possible. We don't have to meet 100% of our heating load. We can get close to it, or maybe the next size up if we don't think it's enough. But again, don't overkill the customer on emergency heat either. And offer dehumidification, because newer units don't dehumidify that well. And sometimes we're just going to have a shortfall that we have to deal with a dehumidifier. The other thing is, I want to reiterate, when we're sizing a unit, we're sizing it for the only time it's hotter than that is like 1% of the summer. There are a lot of hours during the summer where even the best, most aggressively sized air conditioner is still going to be oversized. But your dehumidification load is still there. We're going to go over dehumidification load in a few minutes. But that's why I offer a dehumidification option on every equipment replacement that I do. Heating dominant loads, so colder climates, you're probably going to be using a variable speed heat pump. Use a cold climate heat pump. Just because it's a variable speed heat pump does not make it a cold climate heat pump. You want to make sure it's rated for that. It has things like a pan heater, so when it goes into defrost, your ice doesn't build up and if it's a side discharge unit, sees up your outdoor fan. It's got other technologies in there to make sure that it can actually run in those cold climates. Or if you want to, you just go back with a furnace and make it a dual fuel unit. I think dual fuel over the next few years is going to be the little stepping stone between where we are now and the electrification that a lot of people rightfully want. I mean, I don't have a problem with heat pumps, electrification, decarbonization, none of that stuff. I don't have a problem with. I just think that dual fuel right now is just a nice stepping stone to get there until we get the industry on board with putting in cold climate heat pumps the right way. Sensible cooling for a heat pump. Obviously, you're sizing this heat pump for heating, so you're going to have to check your part load capacity on cooling and make sure that it can turn down enough. Latent heat, again, have enough. That is always going to be the case with latent heat. You've got to meet your latent heat load. And again, you can apply 50% of your excess latent towards sensible. Gas heat, if it's a dual fuel or if you're just putting in a furnace back where a furnace was, just have enough. And I guarantee you most furnaces you're ripping out are going to be oversized. So go back with a smaller size. The ductwork is probably undersized anyway, so you'd be doing it a favor. Heat pump heat, size for heating, have enough. Supplemental heat only as needed if you need it. Emergency heat, stage if possible, 90% of the heating load. Again, you may even decide that you're not going to use emergency heat. I'm just not doing a lot of work in cold climate, so I'm not going to have a strong opinion on whether to use emergency heat or not. I'd love to hear some input from you, Russ, on that. Offer dehumidification, because chances are your cold climate heat pump will not be able to turn down enough to handle the latent load, or as we'll see in a future slide, they do not publish their latent capacity at those conditions. And so you have no idea what it's going to do. And in that case, you need to offer a dehumidification to protect yourself. Heating and air conditioning units are rated by the AHRI organization, and they rate them at a certain set of conditions. Those are not the conditions that you plug into your Manual S. You need to use your ACA design conditions, and they are very different sometimes. So AHRI conditions, they're 80-degree dry bulb, 67-degree wet bulb. That's a lot. That's pretty hot and humid. It's at 95 degrees outdoor, and they test them at 0.5 total static pressure. That's SEER 2. Years ago, SEER 1, they were testing it at like next to nothing as static pressure. So you really could not use these as realistic conditions. What they don't tell you is your latent versus your sensible coolant, and they don't tell you what your airflow is. But ACA design conditions are actual real life. This is what the owner is going to be living through. So your indoor conditions are going to be that 75 dry bulb, 63 wet bulb. Your outdoor temperature is going to depend on your climate. You're going to select a unit. The airflow and the total static pressure depends on the equipment that you select. You got to make sure your unit can move that airflow at the static pressure. And you're going to need to know what your sensible and latent capacity are. So when you're plugging in your equipment numbers, unless your outdoor design conditions happen to be really close to 95 degrees outside, and even then, your indoor design conditions are way different than AHRI, chances are AHRI numbers are not going to work. The best thing you can do is use selection software. And a lot of the big players have selection software. Anything that's ICP has selection software. So Carrier is one of them. So all those brands have it. That is the preferred way because it's just more accurate and it's quicker. So let's take, for example, this Carrier selection software. We've got a single stage heat pump. Here's our model numbers. These are all editable boxes. We put in maybe a CFM to start out with. We put in our conditions. And so these are conditions where I'm at, Wilmington, North Carolina. These are the conditions I put in. Here's my load. Let's see if this unit is going to meet Manual S. So our load is over 24,000, which means that we're going to be using this set of conditions here. Let's see if it complies. Our total sizing limit, we have to be between 0.9 and 0.15. In this case, our actual capacity is lower than our load, so we need to make sure that's not too low. In this case, the lowest we can go is 22,950. We are slightly below that. So technically, we're undersized. But let's just see if the rest of it complies. Sensible cooling, our capacity is lower than our load. So how low can we go? Well, only 90% of it. 17.1 is as low as we can go. We're below that, so we're not compliant there either. And then our latent cooling, we have to meet our latent load. We actually get really, really close to it. But really, the rest of it is so undersized. I'd be a little bit worried about this unit not being able to keep up. This is considered undersized. So let's try something. Let's bump up the airflow and see whether that gets us to where we need to go. So same design conditions, same unit. Now we have 850 CFMs instead of 600. Let's see if we're compliant. Total load, again, we can go as low as 22,950. We're just below that. Nothing to be alarmed at. I'd still roll with that. Sensible cooling limit, we can go down as low as 17.1. We're actually a little bit above that, so we're good there. So far, so good, right? But look what happened to our latent load, our latent capacity. Our load's 6,500. Our latent capacity dropped to under 5,000. So we're not going to meet our latent load. We are not compliant. This unit is just not going to work. So let's bump up to the 2.5 ton unit here. So this is another matchup. Next size up. Let's see what happens. All right, so go back up one. 20, there's a delay in my mouse here. Hang on. Okay, 22,950 total. We are slightly above that, so we're good so far. Our sensible cooling limit, again, we are somewhere between, we have to be at least 0.9. We are a little bit over that, so we're good here. And finally, our latent capacity is slightly more than our latent load. We're good. I would say this system is right-sized. And so you can use selection software, play around with it a little bit, and get where you need it to be. Now let's talk about heating. We've got a Mitsubishi unit here. Let's say this is in Cincinnati, Ohio. Our winter temperature is 14, our summer is 90. Our heating load is 24,000 BTUs. It's maybe a small house, maybe a high-performance house. All right, so out of this entire chart, the only thing you need to worry about is the 14-degree outdoor conditions. If your outdoor conditions are close to that, but not exactly that, Manual S wants you to interpolate. That's a lot of math. Find something out that's going to be pretty close to it and just roll with it. I'm not a big fan of interpolation unless you have software to do it, just because it takes forever. And then our indoor dry bulb temperature, our design is 70. Why they didn't put 70 on the chart, I don't know, but 68 is pretty close. We just want to see what this unit's going to look like. And when we look at it, our CA, which is our capacity, is 15,243. Our load is 24,000, which means we're going to be running a bunch of strip heat. And the reason why is this is not a cold climate heat pump. So it does not perform very well at 14 degrees. You would need the hyperheat for this. So again, making sure this is a variable speed heat pump, but it's not a cold climate heat pump. There is a difference. That's the lesson I'm trying to teach here, is that we would need a bunch of strip heat. And if we ripped out a furnace and we put in this heat pump, and even though it's only 3 kWs of strip heat, our client may not be very happy with us. Now this is a hyperheat now, but we're talking about cooling again. Cincinnati, Ohio. This is a hyperheat Mitsubishi. A lot of numbers on this chart. What I'm trying to tell you is that if you don't have selection software, you got to use these performance charts. Cross out what doesn't apply to you. All right. So really, we're only worried our outdoor design conditions in Cincinnati is 90. So we're going to be somewhere in between these two columns. And our indoor dry bulb and wet bulb is this line here. So we're only worried about these numbers highlighted right here. Everything else can go away. So don't let these charts intimidate you. Break them down to just the information you need. And as you can see here, now Manual S wants us to interpolate and run it through some formulas here. But when you notice, what are we interpolating? What is in between 23,800 and 23,200? I'm not interpolating that. I'm finding a nice round number that I can deal with. Same thing with Sensible. I'm going between 18,000 and 17,500. I'm just going with 18. And then my latent is just whatever is left. So what I'm getting at is if you can't use software, you're using these charts, it's okay to round. All right. Here are our rules for a variable speed heat pump. Okay. Minimum capacity charts. This is what I was getting at. Sorry. We had 5,500 BTUs of latent. We only had 3,000 of load. That's great, right? We're going to meet our latent load. But remember, this heat pump is not going to be running at full speed at rated frequency in the summertime. It's going to be running at less. And so what you have to do on these variable speed heat pumps is you have to look at their minimum or their turn down. And you're going to find that you're going to have less BTUs doing that. The problem is they don't break it down sensible versus latent. So how do you know what your latent cooling is going to be? You're not. So what do? Again, we're going to break down the chart. You don't know what your latent capacity is. I suggest including a dehumidifier because they're not publishing that information. I don't understand how we're supposed to do this if they don't publish the information. Here is a Bosch performance chart for cooling. This is the Bosch system that I put in my house. A lot of numbers here, right? Man, this looks intimidating. Let's break it down. For one thing, airflow affects sensible latent cooling. The more airflow we have, usually the more sensible we'll get and the less latent that we'll get. Bosch is a little bit different because of how they control the compressor, but that's most systems. So out of this entire chart, this is all the information that we need. We only want what the performance is. My design conditions is 90 degrees. So this is 85, this is 95. I'm looking for what's in between. And I want to know that at various airflows. But out of this entire chart, I only need a few little boxes out of here. So don't let these charts intimidate you. In fact, what I suggest that you do is take this information and build your own spreadsheet. If you don't have selection software, I've built a spreadsheet with the Bosch units that I sell. And I go all the way from 2-ton all the way to 5-ton. I've got all the airflows here. I've got all the sensible latent and total BTUs, sensible heat ratios. I've even got my KW, my heating COP. I've even taken the air handlers and I've put in the static pressure and the speed tap that it'll take to make that CFM. So now when I've got a load, let's say I've got 25,500 total load, I'm really going to start looking at sensible load. I don't pay a lot of attention to our total load. I'm going to look at sensible, and I'm going to find the smallest unit that will meet that sensible load, and I'm going to start there. So what does that do? Well, here's the smallest unit that will meet that sensible load. It's our little 2-ton air handler. This is a 3-ton condensing unit, but you can flip the dip switch and it turns into a 2-ton unit. And this is our load. Now, is this compliant? Well, we're pretty close on sensible. We're good. We're actually a little bit more on latent. We're good there. Our heating load doesn't quite make it, but we knew that was going to happen. We'll just throw in a little bit of strip heat, and that looks pretty good, right? That is very aggressively sized. And this would be fine to put in. The only thing that I would say kind of gives me pause, and the only reason why I didn't put this matchup in my house, is that I am maxing out my blower and I'm still having to run 0.6 static pressure. What would happen if I just went to the next air handler size up? My condensing unit stays the same. And I just went to the next size air handler up. Now all of a sudden I can meet manual S and I'm using speed tap 4 and I've got a lower static pressure. So aggressively sizing is encouraged, but again, you just want to make sure that you're not completely maxing out a unit. And so if anything happens, if we have to run ductwork in a different way, that we have no way of bumping that up and getting a little more capacity out of it. Either one of these matchups would have been fine. There's no wrong answers between the two. That was just the reasoning that I went when I selected this matchup. But I've created a spreadsheet here for the Bosch units that I sell. That way I can quickly at a glance if just know what my numbers are. Because these are the numbers you're going to have to put in Quick Model. Let's go to dehumidifier sizing. I like Santa Fe dehumidifiers. These are not all the models, but these are mostly the models you're going to be choosing from. There's 5 of them. you're probably going to be stuck deciding between two of them. But there's only 5 to begin with, so do not let this thing whoop your butt. I recently wrote an article for HVAC School, how to properly size a dehumidifier. Kind of showed a few little tricks and tips. Some of the purists out there had an absolute conniption when I said a few things. That's okay. They're allowed to do that. But take a minute, go on HVAC School, read the article. Essentially, what we're talking about is decoupling the latent load. We want the dehumidifier to handle as much of the latent load as we can within some limits. There are 2 different outdoor conditions we need to talk about. This is the one you do your manual J on. This is the 1% dry bulb. We've been talking about it all evening long. But when you size a dehumidifier, you really need to be using a different one. This is called the dehumidification dew point mean coincidental dry bulb. This is the acronym for short, and that's what we use for sizing dehumidifiers for peak dehumidification load. So this is our peak dehumidification design conditions. So if you've never been to this website before, this is a free website, and you can get all your outdoor conditions for pretty much anywhere that you live. There's going to be a weather station nearby. Notice for me, Wilmington, North Carolina, this is what I did my manual J for. 91 dry bulb, 77 wet bulb. This is what I designed my air conditioning for. Now, when you convert that to dew point, it's a 72-degree dew point. It's pretty high. But when we're looking at our peak dehumidification, we're looking at these conditions here. And notice what that is. It's actually a cooler, it's only 82 degrees compared to 91, and the dew point is almost 77 degrees. So the lesson here that you need to understand is that the most humid times of the year are often not the most hottest days of the year. A lot of times you'll get a lot of humidity, but it's not as hot. Maybe you just had a thunderstorm. Maybe it's just that is how it normally goes. And so when you're trying to figure out what your real dehumidification load is, you need to be using these outdoor conditions. So you would make a copy of your manual J, and you would replace these conditions with these conditions, and you would come up with a latent load. Let's say in this case, we come up with 3,900 BTUs per hour. The formula to convert that to pints per day, which is how we choose dehumidifiers, is you have to divide the latent by 1,054. That gives you pints per hour. You multiply that by 24, you get pints per day. And this is sort of how many pints per day, on average, your dehumidifier needs to remove. We come up with 89. Now let's remember that 89, because now we're going to select a dehumidifier. Which dehumidifier would you select? Well, it seems like that 98 is good, right? It's a little bit over 89, seems like a good choice. The problem is that's not really a 98 pint dehumidifier. In the absence of any OEM information, Manual S tells us that a 98% dehumidifier is only that under these conditions. This is the American, oh God, I had to, something appliance, they rate appliances, and they measure the dehumidification at 80 degrees Fahrenheit and 60% relative humidity. So there's a ton of humidity in the air, and the dehumidifier has a lot of humidity it can pull out. So that's why it's rated at 98 pints. But at manual J conditions, that dehumidifier can't pull anywhere close to that. It can only pull 63.7. Now, what's nice about Santa Fe is that they don't hide that fact from you. They publish it. And notice here the Ultra 98, if we're going with manual J 75 and 50, a little bit of static pressure, it's only down to 65 pints per day. Maybe we say, okay, well, I'm able to tolerate 55% relative humidity. Okay, well, then we can remove 75 pints per day. But we're not removing the 89 that we need to. We're close. But what's probably going to end up happening, we're either going to put an Ultra 120 or we're going to put an Ultra 98, and we're going to tell our customer that their humidity may drift every now and then, but it's going to come back. But just so you understand that these dehumidifiers, the number on them is not the actual pints they remove during actual conditions. All right. Let me turn it over to Russ. Russ is going to show you how we handle in Quick Model Manual S.
All right. Some stuff out of the way here. So I actually don't need a whole lot of time because 90% of what you were talking about happens outside of the software. It happens on a cocktail napkin to the side. And once you decide the equipment that you want, really at this point, the only thing you really need is your airflow and your static pressure so that you can size your ducts to it. And then you size the ducts to ensure that you get that airflow so that you get those capacities from that equipment that you're assuming that hopefully will meet the load. But in Energy Gauge, our load calculation module, here's the loads that we just did. So we have our heating load. We have to meet that number. We have our sensible cooling load, and we have our latent cooling load, and then, of course, our total. So those are the three important numbers that you need to select your equipment. So there's a button down here that says continue to manual S and manual D. So let me click on that. And it takes us to the manual S overview. And right here, if you had multiple systems, there would be multiple, they call them blocks. Okay. So if you have like a block load, if you had multiple systems, there'd be 1, 2, 3, 4, 5 of them here, but this only has one system. So I'll click that manual edit block 1. And then it takes us into the manual S equipment selection. Now, most of this is purely asking for information that's going to show up on a report somewhere. There's only a few really important numbers that actually affect your design at this point. But one of the nice things they do right off the bat is they list all your loads for you. Well, here's your outdoor design conditions because you need those to go into the OEM tables to do your interpolation and stuff like that. So you need your winter dry bulb, your summer dry bulb, your summer wet bulb, and all that good stuff. But here it'll have the indoor temperature, 70, 75, and then your relative humidity. You need that to determine your capacities. And then it's got your loads, your heating, cooling, sensible cooling, latent, and all that. So that's all there. So it's all nice and summarized right in a nice tight little box. But then it gives you the manual S targets that you're looking for. And so the minimum for cooling is 90% of your cooling load. You're actually allowed, according to manual S, to undersize your air conditioner by 10%. You can actually go to 90% of your load. A lot of people don't realize that. So that's your minimum. And then there's 3 other targets depending on whether you're single speed, 2-speed, or variable speed. And at single speed, you're allowed to oversize by 15%. For 2-speed, you're allowed to oversize by 20%. And for variable speed, you're allowed to oversize by 30%. Okay. And there's some wiggle room in there. And the only time that you really have to meet those criteria to the third decimal point is basically if you're being sued is about the only time you ever really have to meet it. But if somebody's really checking your work, we have a few building departments in California that will actually look at all your numbers and check your numbers. There might be rebate programs where they're going to check your numbers. There might be Energy Star or something like that. But if you're just doing it for yourself, my other favorite saying is don't waste time splitting hairs because your job is to shave heads. All right. We need to get through this stuff. We need to be close enough and we need to get going and get through it and not waste a lot of time and money, splitting hairs when we don't need to. So there's a whole bunch of steps. So the first step was to do your load calcs. Step 2 is it's asking for AHRI heating and cooling stuff. So this is, if you click on this is just all your make model numbers and your AHRI numbers and stuff like that. We don't care about that stuff right now. And the only time you would ever have to enter it into the software is if you want it to show up somewhere in a report. If you're not handing that report to anybody, you don't even need to fill out this stuff, okay? And there's a lot of stuff like that in all the software, unfortunately. And then there's your AHRI capacities and efficiencies. So that's just more, I call that encyclopedic information. It really has no bearing on the design. It's just in case somebody wants to know. But here, step 4, this is important stuff. This is the fan information because we still have to design the ducts. So it wants to know what kind of fan. This just shows up on a report, but it's good to say what kind. It wants to know the speeds for heating and cooling. So let's say that cooling's on high on furnaces. It could typically be a lower fan speed. And then Tim, you size your ducts for 700 CFM. So I went ahead and put that in there for both of them. But you could have a lower number for if it's a furnace. Heat pumps tend to both run on the same speed. It depends. It depends. But and then the static pressure, the external static pressure that you're operating at. So that's where you go and you look at the fan tables and you say, here's my static pressure, here's my airflow. You need both of those numbers. Those numbers are very important to duct sizing. And so that's where they get entered in. Okay. So really, when you're doing this design, what I tell people on your first pass through your manual S stuff, all you really need to plug in at this point is your airflow and your static pressure. And then come back later and fine tune it and add all that other information if you feel like it. Okay. There's a little tool here. Manual S has this thing about entering air temperatures. So the air that's being pulled from the return isn't necessarily the same temperature air that's actually going across the coil. If you have all your returns are up in a hot attic, that air coming out of the house might be 75 degrees, but by the time it hits that coil, it may have gained a lot of heat. Where there's a little tool here to help you do this. And this is a classic example of a long walk for a short beer, because it ends up making a teeny tiny difference in the number and then making a very teeny tiny difference in your OEM capacity tables. But again, if someone's really checking your work, it's good to know that. And so there's a tool here that calculates that for you, and you just hit show suggestions and then use suggestions, and it plugs those numbers in, and then you can use that. So basically, when you're in your OEM tables, instead of using 75 degrees as your indoor dry bulb temperature, this is saying you should use 75.1. Big deal, right? BFD, in my opinion. But occasionally it's a couple degrees. Okay, it just depends on the system, and so it might be something where you need to take that into account. Okay, and then you can plug in your actual OEM numbers after you do all your fancy interpolation stuff, and you get your actual capacities at design conditions. You can plug them in here. Again, this just shows up in a report, but the energy gauge does have a check. It will tell you if something's not complying. Okay. And so that in some ways that's nice, but in other ways it's kind of annoying too, because it'll give you these little error messages. And you're like, I know it's off by a little bit. Don't worry about it. So you just hit ignore. Okay. So I'm not going to put anything in these. But once you plug all this stuff in and you're basically done, there's this print manual S report where it'll actually do all those checks for you, and it will show that you're meeting these numbers up here. So if you have to give that report to a building department or a rebate program or something, it'll document that it all passes for you. Tim mentioned this earlier, that there's a new manual S out now. There is a review copy, and it's just the normative section. If you look at the actual manual S, it's just out of reach here. Only like the first 25 pages of manual S is the normative section. That's the section that gets adopted as code. That's the ANSI approved part. Everything else in manual S, the other 270 pages, is what's called the informative section. And that's just it's just helpful information to do it. Okay. The new normative section has been published, and it is reviewable right now. I think if you go to the ACCA website, there's a link to it there. And so that's like the code language part of manual S. The other part is called the user's guide, and that's being developed right now as we speak, and it should come out pretty soon. So the thing about the new manual S is they spend a lot more time on heat pumps. Instead of having like 2 options for heat pumps, there's like 9 options for heat pumps now, and how you size them, whether you want the heat pump to meet all of the heating load or not, whether you want to try to avoid supplementary electric resistance strip heating and stuff like that. There's a whole bunch more options that come into play, and which makes it a lot more complicated, but it also makes it a lot more flexible too. So there's a lot more ways to meet manual S that are more custom to your climate zone and things like that. So that's actually pretty cool. All right, so that's basically all I have to say about manual S. But I did plug in the 600 or 700 CFM and the 0.5 inches of water column static pressure. So let me just show you what's going to happen to those. I'm going to go back, save work, and return to Quick Model. So when I go back to Quick Model, now it's going to take all my room by room loads back with me. And if I go into the data tab and the room table, you will now see, it would help if I get my stuff out of the way. Um, here's all the rooms. It does show the garage. I can turn the garage off down here by unchecking the unconditioned box. So here's all the rooms in the house. They're all served by the same air handler. It's got the floor areas of volume. I had to go in and say what kind of windows. Manual J only cares about 3 types of rooms: bedrooms, kitchen, and other. That's it. Here's where I put all the people. Here's the total heating load. Here's the sensible cooling load. It's distributed by room. Okay. So it's got each room's load. And what it does is it takes the room load, divides it by the total load, and then gives what's called a fraction. And basically what this is saying, you see the 0.022, that this bathroom is 2.2% of the total load. And these all add up to 1. So it does that for heating. It does the same thing for cooling. And then it uses that number to determine the airflow to each room. So if you take 700 CFM, you take 0.2 or 0.022, that winds up being 16 CFM. Of course, it's just a little bathroom. But some of them are more. So it distributes the air. And now I'm getting into Manual D here just for a little bit. It distributes the air for heating. It distributes the air for cooling to each room, which is different because a heating load may not be the same percentage as a cooling load. But then what it does is it looks at the higher of the 2 for each room, and it puts that in this last column here. So now we know that we want to size the duct to this bathroom to handle 16 CFM, even though in the summer it only needs 5, it needs 16 in the winter. So we want to size it to the higher of the 2. Now, when we do that and we add those up, they total, and sometimes substantially more than what the duct system will ever actually see. The duct system is only going to see 700 CFM at any one time, but we're actually designing it to 902 CFM because of the worst case between the heating and cooling. So it gives you that flexibility. So that's just another sort of safety margin that's built into Manual D. And that's a good thing. That's always a good thing. It's much easier to damper too much air down than it is to boost not enough air up. Okay. So that's what we're going to use to size the ducts. And so that's all I have to say about Manual S at this point. And I'll let Tim go ahead and start on the Manual D stuff.
All right, Russ, thank you. Tell you what, I'm just going to get right into Manual D. If anyone needs to take a break, just do it quickly and just come back. But because of time, I want to give Russ enough time to show the really cool stuff of Manual D, and I've got to run through my presentation. Russ, if you don't mind giving me back the screen, and I'll go ahead and get started with Manual D.
There you go.
Thank you, sir. All right. Okay. Here we go. Manual D is all about duct design. Why it's important? You're seeing these reasons here. It's one of the main issues of comfort problems is airflow. It makes the unit run longer, makes it use more energy, makes it heat exchangers overheat, cooling coils freeze up, compressors flood back, and poorly designed and installed ductwork is hard to fix after the fact. It's also one of the hardest things to read, but it's one of the most important things to read accurately. So our goals as duct designers is to deliver air efficiently, keeping static pressure, motor amps down, keeping velocity low so that the air coming out of the vents is quiet. And I've got a couple of thoughts about air velocity that Russ kind of helped me to appreciate there when we get to that. Static pressure. When we keep static pressure low, things just start to work better. We don't need expensive, high efficiency duct fittings from the sheet metal shop when we can keep our static pressure and our velocity kind of low. And when we don't oversize our ducts, we're not creating more material costs, and so we're more profitable. We get the right amount of air in each room. And a lot of times we don't have to do as much balancing when we properly design a duct system. And comfortably, one of the main rules we want to remember is don't blow air directly on people. But the other flip side of that is we still need to move a little bit of air in the room so that we don't have air stagnation. So the Manual D duct design process, you can't even start it until you've done Manual J and Manual S. And so going back to what Russ brought out about room CFMs, you see installers will come into a house and be like, all right, well, we're going to throw a 6-inch duct over here and 8-inch duct over there. Well, how many CFMs? Well, a lot of times they don't even know that, but sometimes they'll throw out a rule of thumb. Well, 100 CFMs over here and 150 over there. The only way you figure out how many CFMs of air each room needs is if you've done a manual J and a manual S. You've figured out what your equipment is. Only at that point do you know the CFMs. If you're doing it before manual J and manual S are 100% complete, you're guessing. So sometimes you can guess right, and sometimes you might guess really wrong. The duct design steps are shown here. We're not going to spend a lot of time getting down to friction rate because another thing that Russ has taught me is that friction rate is not one of those things that we need to lose hair about. But we're going to go through the process really quick. Rule of thumb, friction rate, a lot of times set the friction rate to 0.1, maybe 0.08 on our duct wheel. There's a reason why it's a rule of thumb, because it works a lot of the time, but it doesn't work all the time. And the few times it doesn't work may be the problem job that just won't go away. So again, here we see our ACA manual D steps. There is a bunch of steps that we have to go through in order to get our friction rate and size of our duct. We just don't set our duct wheel to 0.1. We have to go through all these steps. But again, we want to be balanced with that. Manual D also, when you do it by hand, says you size the duct system for the worst case run, and then all the other runs will be okay. When you use software like Quick Model, you use something called a variable friction rate. And so you don't have to do that. But when you're trying to do it by hand or with a spreadsheet, you don't have any choice but to size your entire duct system based on that one rung that's way out there, the longest run, or maybe the run with the most bends, or the worst case. And so software is a lot better. Let's talk a little bit about what we start out with. Total external static pressure. Friction. Look at the picture on the left. Do you think he's trying to pull through that straw? There's a lot of friction in that straw. What's that doing to the static pressure in his cheeks? He's got a lot of return static pressure, right? On the right, he's trying to blow through restricted trumpet. What do you think that's doing to the static pressure in his cheeks? Really high. So when you have more friction in the ducts, the only other result is that you're going to create a lot of pressure in the ducts when you try to move that same amount of air. So a air handler with no ducts connected to it has no external static pressure, because ducts are external to the air handler. If you don't have anything external to air handler, you don't have any external static pressure. So we would read 0 with a manometer because we don't have anywhere to plug our manometer tubes to. Static pressure is a force that's exerted on all sides of the duct. It is not the force exerted by the velocity of the air going down the duct. So it's being exerted perpendicular to that. And so once we hook up ducts to an air handler and we turn the blower on, we get a positive pressure in the supply duct and a negative pressure in the return duct. And what we're doing is measuring the negative and we're measuring the positive, and we're trying to see how far apart they are. So it's not that we don't subtract the negative from the positive. We're actually dropping the negative and we're adding the two numbers together. Here's what I mean. We got negative 0.2 static pressure in our return, and we got positive 0.3 in the supply. What static pressure doing is counting how many units of pressure we have in between. And it doesn't matter if we have more in the supply and less in the return. As long as we have 5 units of pressure, then our external static pressure is going to be 0.5 in both cases, and our blower is not going to care. It's going to move the same amount of air. So let's take a sample job. This is an older air handler. I meant to update this air handler, but I just ran out of time. This is an older, like a Carrier air handler. Let's say that we've done our manual J, manual S, and we've figured out that we need this FXD 037 blower. And our target CFM is 1200. Well, the only way that blower is going to move 1200 CFMs at 0.5 inches static pressure, which is kind of where we would start with our static pressure, would be if we sped it up all the way to speed tap 5. And there's nothing wrong with that, but it gives us very little room for bumping up the air if we need it. So we may have to go back to manual S, and to get a little bit more I guess, wiggle room, we may have to select another air handler, maybe the next size down. They'll match a 3.5 ton air handler with a 3 ton condensing unit all day long. And notice what happens now with that FXD043. Now we can move actually a little bit more than 1200 CFMs, and we do it with speed tap 3 instead of speed tap 5. So what I started doing when I was contracting is I chose matchups that gave me that flexibility. So I never sold a FXD 037 with a 3 ton unit. I always sold a 043 with a 3 ton because I knew I had that flexibility. So we're just running at speed tap 3 here. That's just a suggestion. But we start out with a static pressure, and a lot of times we'll start out with 0.5, maybe 0.6, and we can consider this as like our paycheck. And when we get paid, especially back in the day, we used to get paid and we go to the bank and we cash it out. Man, it looked like we made, or at least when you look at the gross pay on your check, it looks like you're loaded, right? But then what happens? Well, they take taxes out, you got to pay your bills, right? And that's what happens when we have to subtract component losses from our total static pressure. Our static pressure is our paycheck, our component losses are our bills and taxes. And what's left is very little available static pressure for the duct system. And that's what we have to size the duct system based on, is the available static pressure. So what is a component loss? It's anything that did not come shipped with your air handler. It is a component loss. So things like diffusers, dampers, filters, grills, coils, heaters, anything that did not come shipped with your air handler is a component loss. So things like a case coil. Don't just assume you know what the pressure drop is going to be under the case coil. Look it up. This is another carrier number. Let's say instead of that heat pump, we got a furnace and we're trying to move 1200 CFMs, and we got 3 coils to choose from. Which coil is the one that we're going to want to choose? Well, we may have to go back to manual S to make sure it's going to work, but I'm going to choose that bottom one that's only going to give me a 0.14 pressure drop. Because if I choose the 3617 coil, I've got almost 0.3 inches of pressure drop. I started out with 0.5. There's no way that's going to work. So a lot of times I end up choosing coils that have a very low pressure drop as long as they physically fit in the space that I'm installing them in. Same thing with media filter. I'm big on MERV 13 media filters, but you got to look up the pressure drop. So let's say we're going to put a media filter on that same unit, and our cabinet size is 16 by 20. And so maybe we choose a 16 by 20 media filter that fits that cabinet. But look at what the pressure drop. Again, it's almost 0.3. There's no way that's going to work. So we end up trying to choose the next size up, or a couple sizes up, with going with the 20 by 25. Yes, it requires a duct transition, but our pressure drop is a lot lower. And guess what? We're going to get better filtration out of that filter too. So component losses, again, anything that comes shipped in your air handler has a component loss. So a furnace heat exchanger, is that a component loss? No, it came shipped with the furnace, but the return grill didn't, the media filter didn't, the case coil didn't, the damper didn't, neither did the supply diffuser. And so all these other components have their pressure drop. We have to add them together to come up with our component pressure loss. In this case, it's 0.34. So that only, again, just leaves us with a very little bit of available static pressure. We start out with 0.5, we subtract 0.34. Now, all of a sudden, we only have 0.16. That's what's left for our ducts. And it's the static pressure that we have to build our duct system around. Now, if we don't think that's high enough, we could always bump our total static pressure to 0.6 and give ourselves a little bit more wiggle room. The next step is we got to figure out what our duct lengths are, and this is where software comes in to play, because it's going to calculate a friction rate for each duct run. But essentially, the software is calculating from our longest return to our supply, what is the longest duct run length. Now, when you're doing it by hand, sometimes you have to look at other factors. Sometimes the longest duct run is not the longest one by a tape measure. There's other factors that go in. This slide was from my manual D when I was using the speed sheet, but when you use software, just draw it and it'll do the work for you. But just know that part of the process is knowing how much linear feet of duct that you're running. Then you got fittings, and fittings have an equivalent length. So, for example, this 1A fitting, this collar that comes off of the supply plenum, it is the equivalent of 35 feet of linear straight line duct. And every fitting, a takeoff, an elbow, a transition, everything has an equivalent length. So you're going to have to add all those up and to come up with your total effective length, which is your duct length, your linear length of your ducts, plus all your fittings, that gives you your total effective length. In this case, your project is 270 feet of total effective length. Only then are you ready to calculate friction rate. Friction rate is this: you take your available static pressure. Remember, we calculated that a couple minutes ago. That was 0.16. Multiply it by 100, divide it by total equivalent length, you come up with a friction rate. In this case, it's only 0.06. Now you size your duct versus that friction rate. Now I got to credit Russ for giving me this. Well, he gave me the slide on the right. I put Gary Busey on the left. Sorry, Russ. But this just goes to show that don't get hung up on friction rate, because look at that 120 CFMs. No matter if your friction rate is kind of high at 0.11 or it's all the way down to 0.08, you're still going to have an 8-inch duct no matter what. Now, if you're looking to move 70 CFM, yes, you're kind of split between the 7 and the 6-inch duct, depending on your friction rate. But what I'm getting at is don't get hung up on whether your friction rate is 0.1 or 0.09. And it takes a lot of changes to your duct system to move the friction rate to a point that it actually affects your duct size. So I got to credit Russ for that. I was putting way too much attention. When I taught a manual D class, it took us a half hour to get to this point. But really, get to your friction rate and just understand that there's going to have to be some huge changes in your duct layout to actually change your duct size. So again, just trying to be pragmatic. When you use software, variable friction rate means that each duct run has its own friction rate. So for example, both of these runs, let's say they both have 120 CFMs to them. The one that's really far from the air handler would take probably maybe a 7 or an 8-inch duct. The old manual D manual method or the spreadsheet method, both of these ducts, the really short one that's close to the air handler and the really long one that's far away from the air handler, both would require the same size duct. When in reality, we know good and darn well that we're going to have to damper like crazy that one that's closer to the air handler. But the problem with doing it manually is that you have to size everything for the worst case scenario. So use Quick Model. Quick Model uses variable friction rate. You don't have to worry about it. One duct may be a 7 or an 8. The other one might be a 6, and you can just send it. So again, don't do this by hand. Please just give Russ your money and just get Quick Model and just do it right. All right. The last step is check velocity. And again, Russ has kind of helped me to see that not all things in Manual D are worth losing our hair over. So Manual D does give us some guidelines that we should really watch our, even after we size the duct, that if we look on our duct wheel and our velocity are above these limits, so we're not allowed to go over 900 with supply ducts and not allowed to go over 700 in returns, because they say that you'll have a lot of noise. And I'm with you, Russ. I've never heard noise problems from my trunks or my branches. The noise problems that we hear from ducts is the velocity leaving the return register, the supply register or the return grill. That is the velocity problems we need to worry about. And that's guided by these numbers here, and also knowing some specs about your terminations or your terminals. So again, this is guidelines, but trust me, I've seen ducts that have moved a lot higher velocity than this, and they weren't noisy at the ducts. And think about where ducts are. They're in attics, they're in crawl spaces. Can't hear them anyway. So our target friction rate, according to Manual D, is 0.06 to 0.16. So if we're below 0.06, that's kind of on the low edge. What are some things we can do to bump it up? Well, you're going to have to do a lot to get that up. And so you may have to select more efficient duct fittings with lower equivalent lengths, shorter run-out lengths. So maybe go to the room interior instead of the room exterior. Maybe your air handler is all the way at one end of the house. Maybe you need to move it to a central location to get those lengths down. Try to find ways to save on component losses. And consider just bumping up your target static pressure if your equipment can deliver that airflow. Sometimes that's just what you have to do. And as a last resort, maybe increase the air handler size for a stronger blower. So maybe you've got to change that furnace to the next size up because it can't deliver enough air for your cooling, just like we learned about in Manual S. But that's kind of as a last resort. We, again, want to try to be smart in how we deliver our air. This is a quote from Allison Bales about friction rate, because here's the weird thing about friction rate. The lower the friction rate is, the more friction your ducts have. And so it's kind of counterintuitive. But a great way to think about it is it's the terms of pressure drop allowed. So their friction rate, you're only allowed 0.06 inches of pressure drop. So if you think about it in terms of pressure drop allowed, it makes it a little easier to understand that a low friction rate means that your ducts have actually a lot of friction to them. Best practices, grills and registers. We talked about face velocity. Remember that grill has a certain portion of it that is covered with metal. So just because it's a 16 by 25 grill does not mean that when you do the math and you come up with 466 feet per minute, that once you close the grill door, the louver door on that, that you now have an appropriate amount of velocity. Because usually around, I don't know, 25% or more, you need to look at the specs on that grill to see how much of that is actually free area. The other thing to avoid is those decorative supply registers that homeowners love to buy online. There's usually no engineering information on it. If you agree to put those in for them, then you deserve the callbacks that you're going to get when they don't perform. I like using these curved blades, single throw, one-way throw, sort of commercial grade registers, because I have engineering data that I can look at. I can see how far that air is going to throw, and that is how I designed my house. And just to throw the air up towards the peak of the ceiling and then let my ceiling fan take it from there. I use those curved blade. Try to avoid these decorative ones that don't have any data to them. Some things that you can do to try to save on friction rate is use better fittings. Another thing is, instead of using a 90, if you could use 245s, you're going to save about 10 feet of a total equivalent or of effective length. Not a lot. It's not going to move the needle a lot, but in the aggregate, it might help. Here are some big things, though. Try to avoid these squared elbows, because notice how this elbow here has 80 equivalent length of equivalent feet, and this one with turning vanes is only down to 10. Now, obviously, this one's going to cost more, but that's pretty significant difference there. Another one is using these rounded throat elbows instead of these square ones. Notice how this one, if you can get a nice big rounded throat, if you got the room for it, you're down to 15 compared to 80. Maybe you put some turning vanes in there and now it gets all the way down to 5. So these are some things that could move the needle a lot. So junctions, T-fittings, takeoffs, anytime you do a 90-degree takeoff or a T, there is a lot of equivalent length to that. It is a lot better. You got 100, you got 85. It's a lot better to use a Y fitting. You only got 25. That can move the needle. Same thing with returns. When you're putting a return in, if you can Y it in and you can get these two airstreams merged together as opposed to a T fitting where they just crash into each other, you can pick up some performance there. So in this area here, you got a return, airflow is going that way, airflow is going down. It's hitting that airstream. There's a lot of turbulence there. But if you can get them to merge into one another, it performs a lot better. These junction boxes, they give you some guidance on that. You want to use some straight runs. You don't want to tap into the top or the bottom of the box, only on the sides. And the distance between your first collar and the end of the box needs to be at least 2 diameter sizes of your takeoff. So if this was a 6-inch takeoffs in here, you would need at least 12 inches in between the edge of the box and your first takeoff. Following those rules makes these perform a little bit better, makes that airflow a little bit more predictable. Let's talk about single versus multiple returns. A single main return close to the air handler is recommended. That means that we have a shorter return, lower total effective length. Room to room pressure imbalances are have to be addressed because we don't have a return in every room. So let's say I put my air handler in my house over here. Now, in reality, I put it over here, but let's just say for this example, I put it over here, and I put a single return really close to the unit. That's really good for my duct performance, keeps my friction rate good. But the problem is when these doors close, the main body of the house goes into a negative, and all the rooms behind the doors go into a strong positive. So I could leak conditioned air out and I can pull unconditioned air in. That's not desirable. So the next option is multiple returns. It allows for almost a neutral pressure within the rooms if they're used correctly. And then we can use jumper ducts in rooms without returns to provide sort of a passive return path. So let's look at that. We've got multiple returns in each room. We've got one return each room, multiple in the house. The problem is that's a lot of duct work. It's a more expensive job. Probably this is duct length that's going to be factored into your friction rate and may require you to use larger ducts. That's not always a great idea either. The good thing is it does keep your house neutral. But here's another idea. Maybe use your shorter returns here and use a passive return here. Now we got some guidance on these passive returns because you have a lot of supplies behind this door. You have all these are supplies. So this is going to be a pretty big passive return, but it's kind of the best of both worlds. It controls your room pressure good and it keeps your duct lengths low. We're talking about jumper ducts passive returns. Just because you ran a 6-inch supply in does not mean you can just put a 6-inch jumper duct out. Notice this airflow, 75. This was probably like a 6 or a 7-inch duct. And look what size jumper duct needs to come out of it. A 10-inch jumper duct. So these always end up getting oversized. And they have to be oversized to be correctly sized because you want a really low pressure path out so the air doesn't choose to exfiltrate somewhere else. Best practices flex duct. This is another clip that I stole from Allison Bell's blog. If I give them credit, it's okay though, right? So they did a test on comparing flex duct that was installed properly, strapped correctly, pulled tight versus metal duct. And what you notice, this looks like only one line, but it's actually both sheet metal and stretched flex. They mimic each other so close that if you install flex duct straight, pull it tight, don't let it sag, it actually performs almost identical to sheet metal duct. Versus if you just allow a little bit of compression in it, you can see a really big difference where these start to separate. So if you're going to install flex duct, install it right. Use metal 90s to make your turns. Only run flex straight, pull tight, no sags. Best practices, media filters and return drops. Whoever, if you guys don't follow him on Instagram, he's a great inspiration. He does some great looking work. Let's take this really skinny jeans drop right here. There's a lot of friction loss right here. This is not good. What I liked what Jeff did, yeah, he could have used a rounded throat elbow. The guy that sells his jobs for him doesn't believe in doing that, but at least he used a bigger return drop and at least he tried to use a rounded throat. If I had to choose whether having a rounded here or having rounded here, a rounded throat versus a rounded heel is always better. If it's okay if you're square here, but it's a lot better if you're rounded here. And again, using filter media, sizing up, big old return drop. For the life of me, I do not understand why you see these little skinny return drops. They're just the worst thing. You can pick up a lot of performance just selling a media filter and a larger drop. We do a lot of furnace replacements where we're yanking out at 80%. We're going back to a 90%. But there is some things we need to keep in mind. For one thing, let's say we're going back with a 100,000 BTU furnace. Now, hopefully we're not because we've done a manual J and a manual S, and we realized that 100 BTU furnace was oversized to begin with. But let's say that it wasn't. And notice what our old output was. 80% of 100 is 80,000. Our new output is a lot higher than that because it's more efficient. So we probably should bump this down a little bit. The old temperature rise was 40 to 70, so the midpoint is 55. The new temperature rise, because it's a condensing furnace, our midpoint is 45. So what this means is when we plug in our sensible heat formula, we're going to require, our old furnace required 1346 to deliver the right amount of BTUs. Our new furnace requires 1900. And I bet you our ductwork, if we were put this furnace in with this ductwork, do you think we're going to get 1900 CFMs out of it? No, we probably weren't even getting 1300 out of it. So when you're replacing 80% furnaces with 90%, you've got to look at your ductwork because you're going to need to move more air, and your old ductwork is probably undersized to begin with. And that goes back to fan law 2. If our old furnace moved 1,000 CFMs at 0.6 CFMs and our new unit needs to move 1,200 CFMs, what's our new static pressure and will it work? So our old furnace, this was our old static pressure. We're going to use fan law 2, and I'm sorry I'm rushing right through this, but take a minute and kind of look at this formula. Our new static pressure would have to be 0.86. Can this furnace move 1,200 CFMs at 0.86? No, it cannot. So again, this just goes back to the point when we change equipment, we cannot avoid looking at the ductwork. Yeah. So airflow and duct diagnosis, do a visual inspection. You guys know what's jank and what's not. You're looking for this flex bomb. You're looking for skinny jeans return drops. You're looking for a lot of bends and flex really close to the unit where it makes a big difference. All right, so pay the most attention to ducts closest to the air handler because they're going to have the biggest pressure drop on them. And when it comes to ductwork, you can't polish a turd. You can try to repair bad ductwork, but the best thing is to get the best results to quote a replacement. Let the homeowner decide whether they're going to pay you to do it, but don't just assume that you can make bad ductwork work well with new equipment. You got to be able to guarantee your results, because different motors affect airflow differently. So PSC airflows, when we have an increase in static pressure or in duct friction, our PSC blower just moves less air. It doesn't care. It doesn't speed up. It doesn't attempt to move more air. It just does the same thing it always did. It just moves less air. So that results in poor comfort. Yes, it pulls lower amps, but lower refrigerant pressures, temperatures, your system freezes up, it overheats. So when we open up and we free up some of our ductwork, all of a sudden our friction goes down, our static pressure goes down, and we can actually move more airflow. ECM motors a little bit different. When they see bad ductwork, they don't fix bad ductwork. They just work really hard and they speed up, and they're going to move that 1,200 CFMs you're telling them to move, or they're going to die trying. So there's Lucy. They're just going to speed up and try to keep up. And so that's not a good thing either, because you end up having crazy high static pressures. You might suck the air right through your P-trap, and now your unit doesn't drain good. You consume a lot of energy. Your ECM motor dies prematurely. There's a lot of things that goes on when you do that. So I'm sorry I rushed through that, but we're going to turn it over to Russ because I really think the ductwork feature, quick model, is the coolest feature. So I'm going to stop sharing, and I'm going to turn it over to Russ. And after Russ, we only have like three slides left, so stick around for some concluding comments. But Russ, go ahead.
Awesome. Thanks, Tim. All right. So in quick model for manual D, the first thing to do is just draw your ducts. And what I typically do is I place the air handler. You can move it around. You want to, where's your attic access and where's your platform going to be and all that kind of stuff. And you notice there's a vaulted ceiling here, and you have to be careful with that kind of stuff. But once you place your air handler, the next thing is, where are your registers going to be? So I'm going to click on registers and boots, and you just hold down the Alt key and you click, and it places a boot wherever you want it. And you'll see it casts a little shadow on the floor down there. So it kind of helps you figure out where it is in the room. The tab key will rotate it. You can change the size. You can change the type to be that comes in from the end, or comes in from the side if you want it to, like that, or just the straight, like so. So let me just plop down a few registers really quick. It's funny, one of the most controversial topics when I teach my manual D classes is where to put a register in a room. And people get really uptight about it. I participated in a big study and basically found that it doesn't really matter as long as you size your ducts correctly. There's advantages and disadvantages to where you put a register. If you put it out over the window, you tend to have longer ducts. And so you're spending more money on ducts and you have more resistance. My personal preference is my general rule of thumb is to blow the air the opposite direction that it wants to go. So if you're blowing air into a room, the air wants to leave the room. So if you put the register by the door blowing the opposite direction, it's going to have more mixing. It's going to mix better and it's going to get better. You want the air to mix as quickly as possible. So anyways, I'll just plop down a few registers here and just kind of show you how to draw ducts. It'll draw flex ducts really, really easily. That's if you just place a start collar first. So this is the supply plenum. If I place a start collar there and I want to run a flex duct from here to here, I just highlight both of those and I hit enter and it draws a duct. And that's about as easy as it's going to get. You can move it around. And then that little yellow handle if I hit enter, it's going to turn into a fitting, and the fitting that it will turn into is whatever is shown over here where it says new fitting type. So it currently says TY, which is what I want. So if I hit enter, it's going to turn into a TY, and then I can just extend that out over there. So now I've got the duct coming out and going to a TY like that. Okay, so that's how you draw flex ducts. Super, super easy. You can also draw sheet metal ducts. Basically the same thing. You start with a start collar, which I found that that's not what they call it in all parts of the country. But it's basically a round collar that allows you to connect a round duct to a square box is the start collar. They go by a variety of names. But if you click on sheet metal, and then let's say we want this to be a hard 90, and I click on that and I just hit enter, it starts with a hard 90 and I can point it the direction that I want to go. And then I can have it terminate in let's do a end cap. Okay. So I hit that, hit enter. Now I can stretch that out by clicking on fittings and I can grab it. Come on. Just stretch it all the way across here. I can manually size these ducts right now if I want to. Let's see here. Sheet metal ducts, I can click on that. I can just say, let's just make it a 12 for now. I have it set at defaulting to 8. Okay, and there's an end cap on the end of it. I automatically put that there. And now I can put start collars on the side of this, like so. And then you can put it on the top, on the side, whatever you want. And then now I can connect those start collars to the registers that I've placed. And then you can move things around. Okay, so that's basically how you draw it. It'll draw rectangular ducts as well. We haven't figured out a great way to size rectangular ducts automatically because it's such a personal preference sort of thing, because there's 2 dimensions to worry about. And you can set one of them and then it'll size the other one for you. But we just kind of let people do that manually using a ductulator. But it will size round ducts for you automatically. Okay, so let me open a file that now has everything done. Take a second to load. So once you draw your duct system, Quick Model will take a first best guess at your equivalent lengths of all your fittings, because you've drawn a duct system, so it can calculate the length basically to the nearest inch the way you've drawn it. But you've also put fittings in there. You've put TYs, you've put elbows, you've put takeoffs, you put start collars. So based on how you've drawn it, it creates a list of all those fittings, and it takes a first best guess at the equivalent lengths. Let me turn off these. It'll take a first best guess. So here's the duct system all drawn out. Okay. And so you can see it's got some returns coming off. There's several returns on this end of the house. There's a return back here in the master suite. There's 2 main branches coming down. You can see all the supply registers where they need to be. Okay. So that's the system all drawn out. And based on how it's drawn, if I go up here into the friction rate tab, so remember the 0.5 and the 700 CFM that I plugged into the manual S section? Remember there was that one step forward. I said, this is the only important part that you need to know. Here it is, 0.5 and 700 CFM. So this right here is a condensed version of the Manual D friction rate worksheet. If you've ever seen a Manual D, and I can't get it to focus, come on. But it's the friction rate worksheet. It's got the little graph that, maybe if I hide my face behind it. But anyways, this is a condensed version of that. So you start off with your external static pressure of 0.5. You're trying to move 700 CFM. So the whole point of this is to design a duct system that's not going to exceed a static pressure of 0.5 so that you get your 700 CFM. All right. Well, you start with 0.5. And as Tim mentioned in your taxes, you start losing. They start nitpicking out of your paycheck, and you start losing stuff. I actually bumped your filter up to 0.12. Your supply outlets, your return grills, your dampers. If you've got other sorts of coils and stuff, you can put all that information in there as well. Okay. And then it calculates the friction rate for you. But remember I said it takes a first best guess. So if you click on this TEL, total equivalent length button, it opens up a table that shows each run. So this is each branch going to each room, and it shows there's a register boot, there's a start collar, there's another start collar, and there's what is this? There's a T. Okay, there's a T off of the trunk, and then some of these have 90-degree elbows in them, and then they all have a register boot. So there's a register boot at the beginning up here. So each run, it takes a first best guess at your equivalent lengths. But you can edit this. If you think there's more or less equivalent lengths, you can come in and change each one of these numbers that you want to. But it does a pretty good job right off the bat at taking a first best guess. And if you go all the way to the top, Tim mentioned variable friction rate. So each run has a different friction rate because it's seeing different fittings along the way. So the air that sees a whole bunch of fittings and a long length of duct is going to have a lower friction rate. So if you scan across, you'll see a couple that are 0.07, some that are 0.08. What was the highest one? I think is 0.08. So that's pretty standard. You want to be between 0.06 and 0.18. By the way, Tim, your slide was wrong in that. It's 0.18 is the high end. Your slide's at 0.16. So, and that's straight out of Manual D. And so it'll calculate your friction rates for you. I like to be around 0.1 or just a little bit less. I do mostly all flex designs, and they tend to work out to be right around 0.1. Unless it's a 2-story house and you're going from the attic down to the first floor, then you get a different friction rate. Okay, so once you have all this, then we go into the data tab. It's doing some calculations. I have to get a faster computer for training purposes. And then what it's going to do, so I'm in the data tab and I'm in the duct table. And so here is a list of all of our ducts. So here's each room: master, pantry, walk-in closet, bed 3, et cetera, et cetera. Here's all our rooms. So these are our branches. SB stands for supply branch. It's got to move 56 CFM. It's got a 0.07 friction rate. This is the duct diameter. It'll start off showing numbers of how you've drawn them. If it's rectangular, it'll show the height. It'll show the length in feet. It'll show the velocity. And you can put in the register size. I forgot to mention that. You can actually put in the register sizes if you want to. Doesn't change your design, but but one of the nice things is you can actually print out this table and it'll create like a parts list, a shopping list for you of all your fittings and stuff. But here's all your supply branches. Here's your supply trunks. Because we had multiple returns, we have to assign each room to a return. So if you have multiple returns, you say this room is being served by this return. And that's fairly arbitrary. The only time that it really matters which room you assign to it is if there's a return inside of a room that has a closable door, then you want to assign that room CFM to that return. But otherwise, the air doesn't really care. It's going to go whichever way it needs to go to get to a return, as long as there's no door in the way. Here's all the friction rates. So we have airflow. We've specified it. You drew a flex duct, so it knows that it's flex duct. Okay. You drew metal duct, so it knows it's metal, but you can change these if you want to. And then down here is this little blue magic button that says auto size ducts, and you click on that, and it'll size your ducts for you. I've already clicked on it, so I don't think anything's going to change. But once you size all your ducts, then you can go back. Here's all your trunks, branches, all your return branches, your main return trunk. You can go back to HVAC draw, and now everything is drawn to scale. So it's the proper diameter as shown in the 3D drawing. But you can turn on your labels for your dimensions. You can change the size of the labels if you want them to stand out a little bit more. You can also turn on the CFMs at each register. And so you can use this to sort of go through and check your work. So you got a 5-inch going to 33 CFM, 5-inch to 33, 6-inch going to 58, and there you go. And like Tim says, his supply houses don't carry odd size ducts. So anywhere you see a 7 or a 5, just round up. You could, if you wanted to, you could come back in and just throw a whole bunch of extra equivalent lengths in that run and make it bump up to an 8-inch duct if you wanted to. If you wanted this to show more accurately to what you're actually going to install. But I think it's useful to know that this room only needs a 7-inch, but you're going to install an 8. And so that might mean that you may have to damper that room down. It may get more air than it needs, because air is going to take the path of least resistance. But it's always good to know, because you may get in a situation where an 8-inch won't fit, and you'll say, okay, well, how bad is it going to be if I put in a 6? Well, if you know a 7 is only needed, it's not as bad as downsizing from an 8 to a 6 as from a 7 to a 6. And maybe you can shift some load around and things like that too. So I think it's useful to know the exact size duct that it actually needs. And that's basically it. I mean, you can look at this from any dimension. All the numbers will always point at you. If you wanted to print out a more traditional 2D duct layout, what you do is you click on the top button up here, and that'll look straight down from above. You turn off the rooms so that you can only see the floor plan. You can make the floor plan a little brighter, and you can adjust the size of the labels, and then you take it put it in 2D mode, and there you go. So that's a more traditional, and you can play with the opacity of the various things. If labels overlap, you can move them out of the way like that if you want them, put them in a better spot so that they're not overlapping, like so. And that's it. And then you can take a print screen of this. We actually have a tool, a screenshot tool, where you click on this and you can specify the pixels. You can specify the there's the pixels, the width and height of the pixels of how high the resolution is of your screenshot. So if you need to print it out bigger, you can have more pixels in it. If you're just going to insert it into a Word doc or something, you don't need it to be that big. All right, and that's about it. And I will turn it back over to you, Tim. Oh, let me show you real quick. I think it's worth pointing out because it's actually a fairly new feature. That it was funny. My son is the programmer, and he put it in and didn't tell me about it. I found it by accident. One of our other users asked him to do it, but there is a export parts list down here, and you can it'll save it as a CSV file. that can be opened in a spreadsheet, and then you can sort it and do whatever you want to. So that's a pretty cool feature. All right, that's it. Tim, I'll turn it back over to you.
A question came in, will it run on a Mac?
We have some users that run it on a Mac. It is a Windows-based software. You can run it on a Mac, but it has to be in a virtual machine. We do have some users that do that, and they seem to think it works fine. We've had people try to buy the software and run it on a Mac, and they gave up. They said, no, we want a refund. It was too much work, and I'm not sure why they had so much trouble, but we do have quite a few users. Chris Hughes uses a Mac. Several of our users use a Mac, and it seems to work okay for them. But it is, I used to be a Mac guy, and you have to switch back and forth between your Windows machine, so it is kind of a pain.
Okay.
We're hoping before too terribly long to have a version that will run on a Mac, but it's going to be require a lot of programming to get that to happen. So
Gotcha. Yeah, thank you. All right, I got 3 more slides here, and then we'll conclude. So when we talk about a duct system and a properly designed system, this is a slide from my duct class, but we can really apply this to the entire manual JS&D process. It improves safety, health, comfort, and efficiency. And just because of time, I won't ask for any audience participation, but we used to ask people to say how it would affect each one of these. The safety, health, comfort, efficiency is something that NCI teaches. We should be thinking about it in that order. But really, when we have a good duct system, we're not causing any pressure imbalances and causing furnaces that may be in closets to not be able to draft correctly. It improves health because, again, a good duct system does not depressurize a room and pull pollutants in from nasty places of the house. Comfort, obviously, we know what a duct system does for comfort and for efficiency. So you sell somebody a 22 SEER unit, but you install it with an old duct system. It's sort of like putting monster truck tires on this Prius. Are we really going to get the full efficiency and performance out of that vehicle? No, because we got something that's dragging it down. So here are some of the reasons why maybe we don't do manual JS&D. It's time consuming, at least it used to be. We're not getting paid to do it on a free estimate. Our competition isn't doing it, so why should we? The last unit that was installed that we're ripping out wasn't given any comfort problems. And at the very end, we're making so many assumptions. Are we just making a wild, assumptive guess? Well, some of that may be true. It is time consuming. But the reasons why we should do manual JS&D is that you thought that the process here was time consuming. Callbacks are even more time consuming. If you're not getting paid to do them a free estimate, don't do free estimates. Don't do these for free. There's a way to give somebody a price on something with and acknowledge the fact that that price has to be verified by a proper manual JS&D. But you cannot give them your design services for free unless they commit to the work or give you a deposit or something. So there are ways to get around doing this for free. Don't do it for free. We're not asking you to. Yes, your competition isn't doing it. So yeah, that's exactly the reason why you should, because your competition isn't doing it. New units don't dehumidify as well, so just because the old 12 SEER R22 unit was dehumidifying just fine doesn't mean your new unit will. And it's not really a wild assumptive guess. We're adding some numbers in there so we can call it a scientific wild assumptive guess. We're taking some of the assumptions out of the process. Yes, there's still ranges. Manual J we're not hitting a bottle cap with a rifle, we're hitting a balloon with a shotgun, but you've still got to aim the thing. So that's what this process allows us to do. And the state board requires it to permit. Technically, you have to do it. Whether or not it's getting enforced is a different story, but it's required by load to do it. So that's why we should be going through this process. And again, if you're good at doing it, don't do it for free. No one's asking you to do these things for free. Find a way to build it into your business model. I have. I did it with my last business too, which was more of a contracting business. I didn't do these for free, but every job got one. So best practices summary on new installs, perform the whole ACA process here, starting from manual J. We want to be measuring total external static pressure, total airflow using things like the True Flow grid. I didn't get a chance to talk about that today. Return and supply flow. We just want to be measuring airflow more. And if you just want to start with total external static pressure, that's fine. You get a DG8 from the TEC, and you can use, actually, I got a coupon code. It's TD2024. You can save 8% and you get free shipping. Get a DG8, get the True Flow grid once you can afford it, and start measuring airflow. It'll make your diagnosis that much better. Here we see the DG8 and the True Flow grid. Compare the readings after you install the system and you commission it with what your design was and learn from your mistakes. Figure out, did my unit actually perform? Did my ducts actually perform the way I designed it? If not, why? And then use software. Don't do this by hand. Don't use spreadsheets, and even the ACA speed sheets, which they approve. Those are way too time consuming, a lot of room for error. You've got software that can just really shave it down to a fraction of the time. So I believe that is all our slides, and thank you for listening to the class. Again, thank you, Russ. And I'm gonna stick around for a few minutes. If anyone has any questions for Russ, by all means, we'll do it. We'll kind of consider it as a happy hour. I'm gonna grab a beer and we'll come back and we'll talk a little shop.
Actually, Tim, I put my email in the chat, and unfortunately, I can't stick around. I'm actually having dinner. It's only 6:45 here. I'm having dinner with a couple NCI trainers.
Cool.
Chris and Paul Weibolt are here in town, and I told them I'd have dinner with them. So I'm going to go. So I got to run. Thank you guys very much. There's my email. Feel free to ask me any questions, and I'll be happy to answer them.
Awesome. All right.
Right.
Well, I'll be right back if anybody has any questions about this. All right, who's staying on?
Tim, I have a question if you can hear me.
Yeah.
The duct sizing variable versus, doing it longhand. Could you do it variable longhand, going to each branch?
Yeah.
It can be done that way. Okay.
Oh yeah. Yeah.
Just takes forever, I imagine.
Yeah. You could. I mean,
But that's ultimately what the software is doing, is it's going to each branch and individually and sizing for that branch based on the total equivalent length for that branch.
Yeah. Pretty much. So, yeah, the question is, why would you do it? I mean, using one friction rate is fine. You're just going to have to damper down some ducts potentially. The long duct versus the short run, both of them are going to call for 8-inch ducts. One, you're going to have to damper it down. So as long as your dampers are accessible. But let's say you're doing a duct system and your dampers are in a soffit. By the time you install the air handler and you start the system up, everything's covered up. How do you balance it? That's what kind of scares me.
I got one if you don't mind.
Yeah.
I was trying to get as much training as I could for free. I'm just a one-man shop. My wife handles the books.
Yep.
Uh, Mostly a tech by trade, and I did installs for my uncle back when I used to work for him. So I ran across Edge and
Oh
Janawiak's
yeah.
online training.
Oh yeah.
And what I was trying to figure out is when you're looking at friction rates and things and you're getting to that point in your design, you're looking at ductless mini splits. Like how are you bridging the gap between that friction rate and choosing the right ductless mini splits for rooms? And he's like, hey man, in the beginning of learning all the manual J, D, and S stuff, stay away from mini splits. But I'm like, hey, like I'm a one man shop. It's way easier for me to do those. So I'm
Yeah.
just trying to bridge the gap between all that stuff.
So you're talking about ductless mini splits?
Yeah, so I don't, if I'm looking at a certain friction rate for a room to try and figure out how many CFMs I'm trying to move into that room, it doesn't correlate because I have a ductless mini split. Does that make sense? So should I just be looking at my latent and sensible load and just strictly basing it off of that for the head for each room?
Yeah. So first of all, if you're using ductless mini splits, friction rate and manual D are gone. There's no friction rate to a room anymore because there's no ducts going into that room. So
Yeah.
now you are simply worrying about the sensible, the latent, and the heating requirements of that room. And so ductless mini splits are kind of a weird animal because they are always going to be variable speed. And so you can look at the engineering information on there and figure out what the maximum heating and cooling are and try to size them accordingly. But usually you're heating, in most climates, you're heating BTUs for any room is going to be higher than your cooling BTUs. That's just the way it works out, unless you're down in Florida or the Gulf somewhere. Everywhere else, even here, my heating BTUs are higher than the cooling BTUs, which means that your ductless mini split, you're going to have to size it for heating. So what happens in cooling? Well, the thing starts to turn itself back. And when it does that, the compressor slows down and the airflow does not slow down at the same rate. So the coil temperature goes up. And so it's keeping up with the sensible temperature. It's maintaining the temperature in the room, but it's doing it with a warmer coil. And at least with Mitsubishi, they do not publish how much latent capacity that unit does at those conditions. You're fortunate to get at full load conditions out of Mitsubishi, and they're not the only ones. I'm just picking on them because I do the most work with Mitsubishi, so it's still a sticking point every time I do it. I'm like, I have no idea what the latent capacity of this unit's going to be. And so you end up putting in a dehumidifier in the house, and you duct it into the room where it doesn't blow hot air on somebody. Maybe you blow it right on top of the mini split, so the mini split can at least take that air and immediately cool it. Something like I've done that before. But you end up having to protect yourself with a dehumidifier because you can't count on the mini split to do it for you. I put in a house, and I was listening to the wrong people at the time, wasn't really getting educated. This is probably back 2018, maybe 2019. And I was still under the impression that a high performance, tight envelope house with an ERV would not need a dehumidifier. And I didn't quote one, and the homeowner asked me about it. I'm like, nope, you're gonna be just fine. You've got variable speed, mini splits everywhere. You got an ERV, you're not gonna need dehumidifier. I ended up putting a dehumidifier in for free in that house the first summer. He called me, he's like, dude, it's 72% in here. And by that time I'd started getting educated, and I'm in the back of my mind, I'm like, man, I'm gonna have to end up putting a dehumidifier, and that's what I end up doing. So fool me once. But you just don't want to mess around with that. You just got to protect yourself.
And I think in my climate, we don't see a lot of dehumidification. I'm in Albuquerque, New Mexico, so we're generally looking for water.
Gotcha. Yeah, so that's another animal there. The new Manual S has got some guidance for dry climates.
Okay.
And I can't remember what exactly it is, and it's been a long night, so I couldn't quote it, but there is some guidance for that. But yeah, okay. So really, you're going to end up. What's your heating BTUs versus cooling BTUs there and where you're at, or which one's higher typically?
Um, I think the cooling is a little bit higher.
Okay. Well, that makes it really easy. Just size for cooling, the heating takes care of itself.
Right.
And you don't have moisture to worry about. So actually you're in catbird seat. Whereabouts again, Phoenix?
Oh no, Albuquerque, New Mexico.
Albuquerque. Okay, New Mexico. Gotcha. All right. What's going on, Jason?
Nothing much. Which Jason? I see another one on here.
No, I'm talking to you.
How you been?
Good, man. I recognize the Canyon City cooling before I recognize. I'm bad about recognizing people from their Instagram handles, not their real names.
Same here.
Yeah.
Same here. I'll be sending out that care package soon.
Oh, I hear you. That's good.
Yeah,
I gotta get something together. Um, you said you're a 3X though?
yeah.
Okay. Well,
On the heavy
it might
side.
take me a little while before I can get one of those, but I'll. Yeah.
At 6'4", I hide it well.
Oh yeah. Yeah. Well, I'm only 5'11", and I'm not hiding this 2XL very well right now either. So, yeah. Uh, W. Burns, are you the community college or the tech school instructor? Go ahead and unmute.
Yes. Excuse me, Belmont College.
Yeah. Belmont, where is that?
It's St. Clairsville, Ohio,
Okay.
near Wheeling, West Virginia, across the river
Okay.
on Route 70.
Yep.
Yeah.
I just drove through there back in September. I went up to Measure Quick for training, and I flew up there, then drove back, and I drove, I guess, near there.
Where did you go? I'm sorry.
It was Measure Quick training in, oh my goodness, what part of Ohio was it? Near Akron, I guess, Mogador, Ohio.
Oh, yeah. Sure.
Yeah.
Yeah, that's north of us.
Yeah. But when I drove back, I, crossed over the river and went through West Virginia. Really pretty drive.
Yeah.
So
If you had a motorcycle, it would be
oh
enjoyable.
yeah. Yeah. I was in a rental car. Now the funny story about that was yeah. Now it was just a little Toyota Corolla, but I flew up there from Atlanta, Georgia, because I was visiting my in-laws down there, and so when I booked the flight,
Uh-huh.
I wasn't thinking. I booked a round trip,
There you
and then
go.
I got to thinking. I was like, "Wait a minute! I'm not flying back to Atlanta. I don't have a way home." So I tried to do it, and I could not cancel. The best I could do was get credit with airline, and I could
Oh.
not find a flight back to where I live. So I was like, "Man, I'm just going to drive this rental car." And it was a real pretty drive, like 9 hours. It was great. I listened to a
Oh,
bunch
that's
of
cool.
podcasts. Yeah, it was September. The weather was great. Yeah, it was
I've
great.
been driving down to Florida in 13 to 16 hours. It's a killer.
Yeah.
Yeah. 3 months in a row.
Yeah. Well, thank you for enrolling your class in there. I really appreciate that. I had a
we
really good
appreciate
turnout. We had 38 people here.
That's fantastic. They enjoyed it. They get dismissed early. They didn't get to
Yeah.
see the last hour.
Yeah.
But I see you're going to send the recording, so they asked
Yeah.
about that.
I'll send the recording on Monday because I have to re-record the manual J because I forgot to hit record.
Okay.
So I'm gonna have to re-record it and then edit it in the beginning.
I
So
keep thinking if they hear this stuff over and over from different people, it's going to stick.
yeah,
Yeah,
because that works.
I drone on, and it's like
Yeah,
after a while, I think they need to hear this from somebody else.
yeah, it's good. I hear a lot of the same stuff from like the HVAC school podcasts, and you consume content from similar people. They're all going to kind of say a lot of the similar things, but they say it in a different way,
Right.
and sometimes it sticks. I could listen to Russ talk all day long about this stuff. There's so much I could learn from him, but
Yeah. I have a business also, so I work full-time, commercial, industrial.
Oh, wow.
So we didn't get started in the residential. I've been doing it 34 years, and I didn't get started in the residential until about 6, 7 years ago. But
Oh, wow.
I thought, boy, I'm like, I know industrial, I know commercial. I'll know everything about residential, right?
Yeah, it's funny because I started out in residential also, and what I found that I was just becoming a wrench turner, man. You
Yeah.
know, I could yank out a 100 horsepower motor, and I knew how to rig it up and do all that, but I didn't know a lot about HVAC design. And as soon as I decided to get my license, all of a sudden this whole nother world opened up to me, and I lost interest in commercial and industrial really quick when I started learning about design and building science.
I
Because
got lucky and got teamed up with COAD up here in Ohio. It's the Corporation of Ohio Appalachian Development, and they weatherize homes and yank out inefficient furnaces
yep,
and upgrade the homes. And thank God they trained me. And it was just at the beginning of starting residential, because there was, you know, worst case depressurization, CAS zones,
yeah,
blower door testing. I know any of that stuff.
yep,
And it's a whole, I think the residential is more technical than the commercial and industrial. I
yep.
really do.
Yeah, I agree. When I started my business, I immediately, a couple of my industrial customers followed me over because they didn't like how they were being taken care of by
Yeah.
whoever replaced me. So they called me out of the blue, said, "Hey man, you want to come take care of our plant?" Great. And that's why I had started hiring people and all that. But I had started doing residential, just fell in my lap. I had no intention of doing residential because like, oh, the money's in industrial. But man, the residential just falls in your lap because nobody knows what they're doing.
Well, we start out like that, getting plant engineers and,
Yeah.
plant managers and people that, they think because we're doing such a great job at a plant, we know all about residential, but we don't.
Yeah.
And so I had to learn it. And
That was another good thing about doing commercial industrial because every commercial customer also had a house.
yeah,
And once you got one, you got the next.
that's right. That's right.
Yeah.
And we didn't even consider ourselves a residential
Right.
contractor for all them years, but we got serious about it about 6 years ago.
Gotcha.
But I bought Quick Model last year after the Vegas show. Actually 2 years ago, I was at the Vegas show, but last year I bought the Quick Model, and I'm stumbling around. I must not be that good at computers because I mean I'm not good at asking questions on emails and stuff and then waiting for answers
Yeah.
and I'm having trouble. I had basements and crawl spaces, and I didn't even know you had to put dirt around the damn basement. You had to put blocks of dirt around the basement.
I didn't know that.
Yeah, well, I finally learned that. But then I don't use it for quite a while because then I get so busy in the business and I only get a house to do once in a while. And I'm like,
Yeah.
I'm starting at square one again.
Yeah.
I'm curious though. I wanted to ask Russ how much that affected it. Like he started talking about, how small effects certain things have, and I was curious about things like that, like earth around the basement, and
I
if how
bet
much
you
it affected the load
it would
count.
help your heating load because you wouldn't get the loss as like if it was like a crawl space because that dirt is your temperature difference. It's only 55 degrees in the dirt.
Right.
And,
That's right.
yeah, that's interesting. I have not gotten started with quick. I love watching it being used, the
Me
3D. But I went through about 12 years ago the whole learning curve from using. Well, we're still recording here, so I have to call it wrong soft. Um,
Yeah.
and I'm a 90s kid, so I'm used to Windows 91 and something looking like Oregon Trail. Like to me, that's just retro, and I'm fine with it.
Me too.
And now that I've learned wrong soft, I mean, I'm good at it now, and so it's hard for me to just like, all right, I'm going to learn quick model but I will eventually do it. I just need to
Yeah.
buckle down
Me
and do it.
too.
And I would much rather give Russ my money than give wrong soft my money.
Yeah,
You
me
know,
too.
it just because they do nothing else for the industry, especially ever since Alex left. like he left because they didn't really care about the HVAC industry. They're more interested in helping builders.
Yeah.
And so I every time I cut that check every October when my license comes up for renewal, I'm like, oh, this feels so wrong.
It's a big
But
check too.
yeah, I think they just raised their rates. So next year it may be October when I actually uh, switch over to Russ because that's when my wrong soft registration.
You should have seen these top 9 students perk up as soon as that first when he opened up QuickBall,
Yep.
they all sat up in their seats. I'm like,
Yep.
and now they're asking me, can we get that? So I text Russ, and last year he let me get it for the students for
Yeah.
a trial period, and he's going to let me do that again with these students because their ears perked up. I was like, wow.
There's something about it. It feels new. I had a couple of millennials for employees, and I was trying to get one of them that seemed kind of into this kind of stuff to start doing my load calcs for me. And I opened up Wrong Soft, and it was like he was like, it's just a generational thing. You're not going to get somebody to be interested in using it.
Uh,
Yeah, I mean, quick model, it feels like Minecraft.
Yeah.
And these kids are all about it. So that's a great thing.
yeah,
Yeah.
you're right. I appreciate your time tonight, and
Oh yeah.
it's 10 o'clock. Well, yeah, you're in the same time zone.
Yeah, yeah.
And I got an hour drive, so I'm gonna head up the river, and I
I hear you.
appreciate everything tonight.
Yeah, I
Thank you,
appreciate it. What's your first name?
Bill.
Bill? Okay.
Yeah,
Nice meeting you, Bill.
William. W is for William. But,
Yeah. Gotcha.
yeah, they
Yeah.
give you an email here that's W Burns, and then at Belmont College. So
So are you in Ohio or excuse me, West Virginia?
I grew up in West Virginia, but I
Okay.
live in Ohio. I'm up by Steubenville, Ohio, north
Okay.
of in Toronto, out by Austin Lake Campground.
Okay. Yeah. I think Nate Adams lives around your area. Do you know, have you ever,
That's
you know who Nate is?
is he an electrician? That's a
No, he's like a building science guru
oh
in
no, I don't
the
know him.
Ohio, West Virginia area. I know.
I don't know him. No,
Okay. Yeah, he does a lot of building science stuff online. Super smart dude. So,
I'd like to connect with someone like that.
oh yeah.
It's local and
Well, look him up on LinkedIn.
okay.
Yeah, he's a smart dude. So,
Appreciate it.
yeah. Well, anybody else got any questions or?
One more thing I was curious about
Yeah.
was spray foam insulation. I noticed on your chart, that your curve started dropping off as you got into higher ratings, but I mean, clearly we see massive differences in calculations with spray foam homes.
Yeah.
But does Manual J have a spray foam R designation?
It is called an encapsulated attic, and then you tell it what the R value is for the insulation, the spray foam. So it doesn't carry that spray foam. It could be rock wool, it could be anything. But you just need to tell it what the R value is and that it's on the roof deck. And once you say that it's on the roof deck, now, of course, you got to include your attic as sort of a semi-conditioned space.
Right, conditioned space, yeah.
Yeah, and that's kind of a weird one too because I don't actively cool and heat my attic. Because I don't want to exchange any air with my attic. I don't want to breathe spray foam. I think the jury's still out on how safe
VOCs.
it actually is. I mean, I've gone up there with my air quality stuff, and I've pushed on because I've got open cell, so you can push on it. It's pretty spongy, and I don't read anything, but I just don't know. So I just have a dehumidifier that keeps it dry. That's the only thing you need to worry about is making sure you keep it dry.
Yeah.
And then, so I'm not actively cooling it. It's a few degrees warmer in the summer, and in the winter, it feels great up there. All the heat just rises. Like that's where all my heat's going is up there, and so it's actually like several degrees warmer up there. But the only thing you got to worry about is keeping it dry. But yeah, I know on Wrong Soft, I can model it and I include the condition, I guess that attic area as part of the conditioned space, but I'm not trying to maintain 75 degrees up there. I care less what it is.
Yeah. So So is the R value then based on the thickness on that
Mhm.
on the open cell or closed cell? Is that how that works?
Yeah, it's per inch. Open cell's about 3.7 per inch.
Oh, okay. I
And
guess that's
so
what I didn't
then the
know.
question is,
I was asking.
for the meth head that came out and spray foamed it, how thick did he do it?
Yeah.
Because he takes his job seriously, right?
Yeah.
So
Of
yeah,
course,
you just don't know.
around here we're seeing a lot even in walls, and they just scrape it
Yeah.
even with the
Oh yeah.
studs. So
Yeah, it's great. If I could have afforded it, I would have put it in my walls because it has an air sealing
yeah, and
element
I
to it
think maybe
also.
probably that's probably one of the biggest changes that you end up with as far as the tightness. Which I don't know. On your thing, it was crazy how much of a difference it went from tight to completely loose, but then not much in between. But still, it was.
Yeah. Yeah, I mean, when I built my house, I decided to use the zip system sheathing
Oh yeah.
to achieve my air sealing on the walls, and that
Mhm.
that made me feel a bit better about just putting bats in there. But for my attic, the only reason why I wanted the spray foam was because I couldn't afford the zip system or the Advantex, which is their brand of roof sheathing for the roof. I just couldn't afford it, and I felt like I was gonna. Plus, I had to think about the installers too. Not a lot of people know how to do zip system
Yep.
right.
Yep. It's
It was
very.
a hard enough time for me to get the framers to actually roll the tape. Like I had to call my builder and tell them if they don't come out here tomorrow, they're gonna have to rip all the tape down and redo it because it's already rained once. And I told him, I was like, we're not going any step further until this gets rolled. And they finally came out and he did it. I
Huh.
can't imagine if I would have had to deal with that with roof, where I couldn't actually go up on the roof and check all of it. I just didn't want to deal with it. So spray foam worked out pretty good. I just know that I have exactly 15 minutes to get out of the house if my house catches on fire before,
That stuff is pretty flammable. That spray foam, it's insane.
yeah. Yeah, there was a guy that argued with me on LinkedIn about it because I kind of made a joke about that. It's like I have exactly 15 minutes before, and he's a spray foam rep or something. And he was like, "You have to think about it as an assembly, like because they put like some kind of flame retardant on there." And
Mm-mm.
I'm like, "Yeah, but that's only if you know it's been put on there, right? Once it gets past the flame retardant, it's like liquid gasoline, dude. Like, I know
I
if
didn't
your
realize
house
how
catches
flammable
on
it
fire, I
was.
better wake up."
I didn't realize how flammable it was until I was brazing a refrigerant line near it, and it lit up pretty quick.
Yeah. So. Uh, Yeah, we just know we got good smoke detectors in the house, and see you, Bill. Yeah. Other than that, I mean, it's good. The other thing I learned about it is like it air seals pretty good, but open cell will bleed, and when you spray foam it to wood, air can leak in between it and the wood and like in
Hmm.
the little crevices
Yeah.
because we smoked my house after when we blower door tested it.
Hmm.
So after the spray foam went in before the sheetrock, we pressurized the house with the blower door and we got a smoke gun or smoke theatrical smoke little tube and started smoking the house. And it was crazy. It was coming out the eaves where the spray foam was sprayed up against where my walls came in. That gap right there,
Huh.
we were leaking. And so I had to go in there and touch it up with regular like spray foam out of a can before they covered it all up.
Wow.
But yeah, it's crazy. Yeah. Well, anyway,
Thanks again for everything.
yeah, thank you. Thank everybody. And this recording will come out sometime Monday afternoon. So thank you for your patience on that. Go ahead and close the room down and you guys be safe.
Good night.
So make sure I'm not missing any comments here. Yeah. All right, cool.